Well, let's start. Oh, this is the building, our old picture. Now those trees here in front of it, they are grown. Well, let's talk about sintering. Of course, it's out of format. No, it's okay. Not so bad. I changed it a little bit, but we can obtain, as everybody knows already, nice microstructure when we crystallize glass. By crystallizing the volume of the glass, we can achieve fine submicrometric crystals. This is a commercial glass ceramic from Corning that has high thermal shock resistance. And to show an example, we have regular dispersion of crystals. We have a residual glass that we can use to control the property, mixing the properties of the glass and the crystalline phase to control the properties of the final glass ceramics. And we are able to produce ceramic free of pores that is very difficult to achieve when we start from the powder. The glass ceramic by volume crystallization, this is traditional method. We start from the powder, mix the raw materials. In general, we have to add nucleation agents, melt, homogenize in the liquid state. Then we form a viscous liquid that is formed in the final shape from the molten state. After this glass article pass through a heat treatment for crystallization, controlled crystallization, and we have a glass ceramic. The heat treatment, if we see here, we have a DSC curve, and the blue one is of a fragment of glass. We see TG, glass transition, we see crystallization here, and here we see melting. And after TG, normally the nucleation treatment is performed. And in a higher temperature, the nucleated material or glass is led for crystal growth. And the treatment is around TG and below, of course, the melting the temperature. And in general, it's below the maximum crystal growth, maximum peak of DSC for crystallization. Well, volumetric crystallization has more or less this picture here. We first have to nucleate the glass, or those nuclei come from the addition of nucleation agent to glass composition. Then they are let to grow. When they touch the neighbors, we have a grain boundary, and we have a microstructure that is a mix of a residual glass and some crystals. Those crystals can be managed to be out of the same size or with a size distribution, depending how you prepare or perform the high temperature heat treatments for nucleation and growth. Okay? The microstructures can change as if you, for example, let the glass in a long nucleation time. Oh, I'm sorry. Or you add a lot of nucleation agents, then you have a lot of nuclei that when they grow fast, they hit to the neighbors So we have fine or small nuclei, small grains in the microstructures. You can manage to let the material to nucleate during a short time, or add a low amount of nucleation agents, and then you have only a few grains that can grow more in the microstructure. So it's possible to control what's nice in glass ceramics. That's possible to control the microstructure, controlling the glass composition, the amount of nucleation agents, the heat treatments for nucleation and growth. Well, these are some examples of applications of glass ceramics obtained by volume crystallization. Don't stay here too long. But we have advantages and disadvantages when you follow this path. The advantages, some of that I remember, of course, are it's possible to obtain complex compositions as a single glass phase. That's interesting to form from the molten state. It's possible to continuously change the composition and then continuously change properties, and that abilities this material for machine learning and IA prospection, as we have been talking last days. It's possible to assimilate inorganic wastes, and there's a lot of papers in the literature where people use wastes, inorganic wastes, to prepare glass ceramics for us, mainly for our buildings or civil engineering. The forming is performed in a very high rate. As we know, the glass industry produces a lot in a short time, and possible to control the crystal number, size, and crystallization fraction, controlling the heat treatment and nucleation agents added. It's possible to obtain microstructure free of pores. It's possible to obtain a complex shapes from the glass. The manufacturing has a large scale. Some disadvantages: forming is limited to suitable glass forming composition and viscosity within strict limits. We have to control the viscosity, we have to control the compositions that are able to produce a glass and so on. It's expensive, the high temperature forming needed. Often we need add nucleation agents that are difficult to find for all compositions. It's not easy to find nucleation agents for all the compositions that are interesting. So we look to another alternative, that is produce the glass ceramic from the powder. We first produce a glass and then mill it to get a powder, and the powder allow us to use the powder technology key that is more used for traditional ceramic materials. Yeah? From this path, we mix the raw materials as in the other process, but now we don't need to add nucleation agents, because those nucleation agents, the crystallization can start from the glass surface. And when we have a powder, we have a lot of surface in the glass, in the particles compact. Melting, homogenize it, quench the melt. Normally into frits, it's much easier to get the pieces of glass, small fragments of glass. And then we have to classify the particle size, control the granulometry. Having this powder, you may form using traditional ceramic forming. It can be automatic and doesn't need to be an artist way of forming. And then perform heat treatment for sintering and crystallization. And often sintering and crystallization occurs simultaneously. Then we have glass ceramic. Let's see how it works. What's sintering? Sintering is when you have a bunch of particles and you heat treat, you increase the temperature high enough, the particles form a neck in the contact between them, and this neck grows in diameter to decrease the surface energy, changing it into interface of lower energy. And then we have this bunch of particles transformed in a monolith. Okay? This is sintering. So we have the neck formation, and this is a detail important to model the rate of sintering and the densification possible when we have a glass particle compact heat treated. Well, densification is not sintering. We usually hear or read that sintering is when we densify a bunch of particles, a particle compact. But actually, sintering is possible to be obtained without densification. We see here an example. Silicon sinters, we see here in this gray phase, the solid, and in the black phase, the pores that were not eliminated during sintering because the mechanism of material diffusion during sintering follow a surface path, and the center of the particles did not approach in this kind of mechanism. So we sinter without densification. The pores are is still inside the materials. But, of course, we can sinter and densify, removing the pores from the microstructure if the material from the center or the bulk of the particles are transferred for the neck region. And then we can achieve full densification depending the mechanism of sintering. What happens when we have a glass? When we have a glass, the material diffusion to the neck or to the contact between particles occurs by viscous flow. Okay, and here we have some examples. This is a bioglass sintering. Here you see the temperature increasing, okay? And then you have sintering and densification, but we see some pores trapped in the microstructure. Another example. Again, the temperature will start to increase there, and we see sintering causing shrinking because the pores inside the materials are being eliminated from the surface, and we have this shrinking, and the part of the details obtained from the forming process here, probably this 3D printing, is preserved in the microstructure. Well, advantages and disadvantages of using the powder technology. The advantages, it's possible, again, to obtain complex composition as a single glass phase. And it's easier to form or to process if you have a powder of only one composition, compared, for example, when you make a porcelain, we mix feldspar, quartz, clay, different kind of clays. We have to equilibrate how all of those raw materials will behave in the mixture. Here we have only one glass phase. Again, we have possibility to continuously change composition and look for properties using machine learning, IA processes, and so on. Again, it's possible to simulate inorganic glass. And what's nice, in my point of view, is that we may perform forming at room temperature. We don't need to form the material at high temperature at very costly process. This makes this kind of manufacture friend for a small production process. When we think in production of glass, we always need very expensive machines, and it's difficult to handle. You cannot make an office in your house, in your garden, or your backyard, to start a small business producing small pieces of something, for example, sensors. Okay? So this is attractive for this kind of process. You may use interesting forming process like tape casting when you think on batteries and cells. That's interesting. You can think on 3D printing, additive manufacture of complex forms, geometries that are not possible if you by any other forming process. Again, you have only one single glass composition, and no need for nucleation agents, because all the particle surface works as site for heterogeneous nucleation. Okay? And what's written there is that when you melt a glass and form it into frits, you need to cool down only small pieces of glass. So you may extend the range of composition that are possible to obtain as a glass. Because for fragments, you can achieve higher cooling rates than it's possible when you have to form a bulk glass, for example, for a bowl or something like this. But porosity is very difficult to eliminate, of course. And again, not, but what's new here is that you need to sinter before crystallize. If the glass crystallizes too fast, you are not able to sinter or densify. So not all the compositions are possible to obtain as a sintered glass ceramics. And it's important now to think how to model this, because modeling teaches us what are the important variables, process variables. How can we look for better compositions or better properties? For example, here it's not a glass; it is a crystalline ice spheres sintering. You can see the neck forming and the neck diameter growing. And the black dots here are the experimental results. And if you test different models, you can have the luck or as a result of your effort to find one model that explains well what's happening, and at least in a range of temperatures or time, and try to understand why such a model doesn't work for higher temperatures or longer times. So the model teaches us, the model let us allow us to learn what's happening and how to interfere, how to control, how to predict what will happen. In the case of glass viscose sintering, we can use the Frankel model for sintering that considers two spherical particles of same size sintering. This is possible to find in the early stages of sintering. And here we see from the model that the densification or the density after some time in a given temperature will depend, of course, the temperature that controls viscosity, the size of the particles, the surface energy, the time, and the density in the beginning of the process, the relative density in the beginning of the process. In the final stages of sintering, we can use Mackenzie-Shuttleworth model. Now we have a continuous matrix of a viscous liquid with isolated pores, spherical pores of a given size. And again, the densification of the reduction of the diameter of those pores will follow a model, Mackenzie-Shuttleworth model, that again depends on temperature, viscosity at that temperature that's controlled by the glass composition, the pore size, surface tension, time, and the density at the start of the process. But in practice, we don't have spherical particles, of course. We have, in general, we can have spherical particles. For example, Giron has spherical particles. Yeah. But not all people is lucky enough to have spherical particles. In general, we have jagged particles produced by milling, by grounding. We have polydispersed sizes. Of course, you can work to get spherical particles of all of the same size, but in general, if you grind, if you mill, you have a particle size distribution. Okay? You have a particle size distribution. When you have a glass above glass transition, you have crystallization happening at the same time of sintering, happening in the same time of viscous flow from the surface of the particles. And industrially, in general, we have heating path, non-isothermal treatment. So we have to consider all of this when we're thinking to model glass sintering and crystallization. So that's what Miguel Prado, Edgar Zanotto, our friend here, Ralph Miller from Bonn in Berlin, considered some time ago. This paper, this nice paper, is from 2006, or no, 2001, more than 20 years ago, 25 years ago more or less. And what they considered, well, you can think the glass particle compact follow Frankel up to a critical limit, and then it follows Mackenzie-Shuttleworth. Okay? Frankel is something that doesn't work for higher long times because it goes up 100% densification. It's not possible. So we have to have something like this. In the beginning, Frankel, this yellow curve, and after red, the Mackenzie-Shuttleworth. And so we can make it happen for a given particle size, and considering, for example, that at 80% of the relative density, the mechanism of sintering will change from Frankel to Mackenzie-Shuttleworth. But how can we consider a particle size distribution? Their idea was, well, we can imagine that the fine particles are inside the interstices, the pores of the large particle packing, and they all sinter together. So the particles are sintering with particles of the same size. Okay, so we have fine particles sintering together, medium particles sintering together, large particles sintering together, again considering spherical particles in this case. And we can calculate the stage of sinter for this range of particles, if they are in the Frankel stage or if they are in the Mackenzie-Shuttleworth stage, and ponderate by the fraction, the volume fraction of those particles in the particle size distribution, and sum up all of the effects. Well, but they are mixed, and then they consider, I won't explain to you what is this exactly, but these neck-forming abilities, when you have the probability of a given particle size to be next to another given particle size in the distribution. So this is an effort or a suggestion. How can we mix up again the particles and see the effect of mixing the different particle sizes? So this model was successful. It's terrible, we lose format when we change the computer. This is always a problem. But we see here that this model was very successful, actually, to explain how glass particles will sinter. And here, but before here, we only have viscous flow sintering. We were not considering the crystallization from the surface. But crystallization from the surface always happens. Okay? I'm going to show you here. Well, what do we have here? Do you understand? This is the DSC curve of this glass here. There are other glasses in the paper. We are dealing with this one here. This is a bioglass containing 5% lithium. And you see here the temperature, okay? The temperature, the process temperature. You see the particles are jagged, irregular form, of irregular shape, and different sizes. And in the DSC curve, we see TG at about 500 Celsius degree. Then you have crystal growth starting below 600, and you have crystallization occurring in this non-isothermical path up to about 700 Celsius degree. Okay? Oh, let's see what happened. Pay attention here, more or less at 500, the particle will start change the shape, but after some time, you don't see you don't see anymore the neck formed in the contact between particles increasing in diameter, because now you have the surface crystallized, and when you have the surface crystallized, the viscous flows that allow the material transport to the neck doesn't happen anymore. Okay? And that's the reality. Some glasses doesn't crystallize easily, but most of them crystallizes from the surface much easier than they crystallize by homogeneous nucleation. Here we have soda lime silica glass. Here we have a diopside calcium magnesium metasilicate glass. And we see partial sintering, but there are crystals around in the interface between crystals from the surface of those particles. We see crystallization in both cases. We have to consider the crystallization in the model. The crystallization will have the following effect if the densification occurs fast enough, and we have the elimination of the pores and crystallization occurring after. Okay? In this case, we have this kind of microstructure. And how Zanotto, Prado, helped with Half-Miller, solved that problem. They considered that the densification as a function of time of a crystallizing glass will depend the kinetics of surface crystallization and the kinetics of surface crystallization. Here is the densification without crystallization, calculated as showed before. And the kinetics of surface crystallization can be given by, for example, Johnson-Mel, Avramkov, Mogorov kinetics of phase transformation from for the surface. That depends. The density of nucleation sites, the crystal growth rate as a function of temperature and the time. The compact is in the furnace, okay? When you have that happening, you can explain this. The density of the compact saturates, doesn't achieve 100% densification. This is wrong. This is relative density. So you have a residual porosity trapped in the glass ceramic microstructure. This is again the same thing. Okay, I will speed up, but it's the same. You see the crystallization saturating before we are able to achieve 100% densification. This is due surface crystallization. This is more or less the microstructure when we have surface crystallization. The crystals will grow from the surface, and if they grow occupying all the surface, you stop having viscous flow. And then some pores are trapped due to crystallization from the surface. It depends, of course, the kinetics of crystallization. If it crystallizes too fast, you eventually you don't have any sintering. You have a powder in the beginning of the process, you have a powder in the end of the powder, but before you had a glass powder, now you have a crystalline powder, okay? Well, but if we are successful to densify, we can produce very interesting glass ceramics from sintering. This is a commercial example from Nippon Electric Glass, Neoparis, that's used for buildings. And we see here that even coarse crystallized grains, here we have some millimeters in the scale, are interesting, and in this case, it gives to the material a natural, how to say, a pure, esqueci a palavra. Appearance, yes, appearance, mimicking granite, marble, natural rocks. And you can see this application of these nice materials, curved, walls and facades and so on. We'll skip this. But when we're trying to make glass sintering to produce a sintered glass ceramic, we have to worry about something. For example, when you have a very large difference between the glass density and the crystal density, you don't have material to complete the crystallization of the grain up to the center, because the glass is shrinking with the crystallized surface layer from this particle surface. And then you have the nucleation and growth of a pore inside each particle, due to the difference of the density of glass and crystalline phases of the same composition. That was explained by our dear Vladimir Fokin, that is present here in a very nice paper, together with Professor Zanotto also. Okay? Another problem. Here you see the crystallization is too fast that we cannot densify the pores inside intergranular particles. You see pores here. They are filled with the resin used to prepare the samples. So we have very poor densification in this case, and again, you have pores inside, spherical pores inside each particle. But we also have other problems. When the thermal expansion coefficient of the phases are too different, or you have a higher degree of difference of the thermal expansion coefficient depending the crystalline, depending the crystal directions, you have cracks. Cracks can appear in the microstructure due to the difference of retraction in the grains. So this is another problem, that when you're trying to make a glass ceramic by sintering, or not by sintering, even by the volume crystallization, you have to worry about this. Again, here you see cracks showing due to the difference of thermal expansion coefficient between the glass and the crystalline phase. Okay? Here inside the grains, you also have cracks that decreases the strength of the material. So we are first looking for nice properties, properties given by the composition, by the crystalline phase that we are trying to crystallize in the glass ceramic. But actually, we have very often to worry about the difference of the glass density and crystal density, the difference of thermal expansion coefficient between the phases. And so it's complex to get a successful glass ceramic, even by volume crystallization, but also for sintering. But if you're successful, you can produce some nice materials. In the literature, we find a lot of examples of sintered glass ceramics for scaffolds, biomaterials. We have glass ceramic for tiles produced by sintering root, with the appearance of natural rocks. You can produce fine crystallization, also fine-grained materials using this process, and so on. And what's nice in my point of view is the possibility to make 3D printing. 3D printing is a promising route for from the glass powder, okay? This is Anna Carolina, that's arriving from Italy. And another interesting possibility that is pursued by our colleagues here, Isabella and João, is the flash sintering of glass powders. What we're pursuing is to make the sintering very, 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 very fast. Okay? If you don't control, you will explode the sample, destroy the sample, and nothing will be produced, actually. But if you are able to control the electrical current passing through the material, you can get very fast shrinking, very fast densification. And now you have to pay attention because nothing much happened. You're going to see here a reddish, a red color due to heating, and shrinking will occur very fast. Okay, that's controlled flash sintering. We modeled that, and that's it. Okay. In time. Thank you for all. Thank you for our sponsors. Thank you very much.
Thank you very much, Edu, for this great overview on the topic of sintering. And the talk is now open for discussion, questions. Yes.
Hello, good morning. I'm Caroline. I'm from University of São Paulo. And my question is related to how we can find the melting point if there is an experiment when we have a new composition of the glass. And another question is about the TG. Is experimental too?
Yeah, TG, well, if you perform a DSC analysis or dilatometry, you can find TG easily.
No, yes, but usually I was paying attention in other presentation. They do annealing after the sintering. But if you're going to make a TG, this is going to influence the analysis.
Yeah, of course. If you crystallize, you cannot measure TG anymore. So you have to measure TG before treating for sintering and crystallization. Then you have this temperature as a reference to design your heat treatment and look for what's the best heat treatment for sintering and densification. And melting, if you're lucky enough to see crystallization during the DSC, you go at higher temperatures. This crystalline phase will melt, okay? And then you can characterize melting temperature or liquids. But if you have a liquidus, a glass or a composition that is reluctant to crystallize, it doesn't crystallize during the DSC analysis, then it's tricky. People use gradient furnaces and let the sample, a long bar sample in the furnace for a lot of days, and then you go to the microscope and look in what temperature you don't see crystals anymore, and then you have a liquidus approximately. And we suggested another method. If you grind very, very finely the powder, then you have a lot of surface that is catalyzed crystallization from the surface. Then if you know TG, you let a little bit above TG for a long time to crystallize at least some. And then you perform a DSC analysis to melt that crystallized amount. So you see liquidus.
Yeah, because I was
we
thinking...
have a paper if you want.
Okay, please send me. But because I was thinking if the annealing process is to relieve the internal tension, and if we skip this to do the DSC analysis, like For me, it's
the
like
annealing, the release of residual stresses doesn't, of course, for Ricardo, for example, it will interfere where TGE or fictive temperature is, but for practical applications, the release of stresses won't limit you to obtain the glass transition. Okay?
Okay, thank you.
There's some guys here. Deixa eu tirar.
Hello, good morning. I was just wondering that you showed a picture that there are two mechanisms of Frenkel and Schwarzson. I don't know that the pronunciation.
Mackenzie Shuttleworth.
Yes. And you explain us that it depends on the time of transition that the mechanisms are changed. But after that, you model it in the way that you're sorted by the particle size. But maybe in the group of the particle size, how we know that all the particles are, in the mechanism, because you divided them to the two mechanisms and try to calculate the formula. But I can understand that how you divided the part, because it wasn't dependent on particle size.
Yeah, depended on the
depended
particle
on
size.
time.
Yes.
And then there was another model that you again developed, but again it wasn't about this time of transition and the mechanism. You told that in the surface of the glass we are starting the crystallization, but in another developed formula, I think that it was in slide number 32, you
I'd remove it.
you are averaging the crystallization in whole the glass.
Yes.
If I understanding.
I think I understood. Well, the passage from the Frenkel to Mackenzie Shuttleworth will depend on the particle size. So you have to calculate for each range of particle size in the particle size distribution when it will pass. We consider 80% of densification. That's the limit known for Frenkel to work. So we use that arbitrarily, a little bit arbitrarily, to pass from Frenkel Mackenzie Shuttleworth. And you have to calculate for each particle size range, small range. And when you have crystallization, sometimes you crystallize the surface before achieving this critical density. And then you don't achieve Mackenzie Shuttleworth. You stay in a low relative density below 80% forever, because you don't have viscous flow anymore. Okay?
Hi, thank you for the wonderful talk. My name is Alexander from Alfred University. I was mostly just curious, have you had a chance to compare the microstructure of some of these sintered compacts to traditional powdered sinters, starting from a ceramic compact? And then also, have you observed any weird microstructures, especially at those necking points, especially if you have crystallization near when that neck is forming? I'm curious if you see anything weird happening there on the surface.
Mm-hmm. Do you remember the two spheres with crystals?
Yeah, it's hard to remember.
That is, I think it's an example of this. You don't have full crystallization of the surface, but you already limited the shrinking, because it's crystallized enough to avoid the viscous flow to the neck. Okay, so we see. It's not difficult to see that happening oftenly. I think that's it, or you made another question that I forgot.
It was just if you've done a comparison of the microstructure and if you see any substantial differences in the grain size and shape, that sort of thing.
Yes, we do have differences, because when you start from the powder, you have these crystals growing around what was the grain, the glass grain, inside the particle center. So you have a cellular microstructure or dispersion of crystals or so, something like this. It's really different. But if you densify to the most possible limit completely before crystallization, then the crystallization approaches what you would expect of volume crystallization if the particles are fine enough, but you will find some pores in the microstructure.
Actually, I'd like to follow up on the question, the first question you received about the appearance of sintering in a DSC. It should show up as an exotherm, right?
Yes,
Because,
it's
yeah.
an
And so
exotherm.
it will overlap the glass transition, or will it appear before the glass transition?
Never before. It depends the composition for metal glasses. It can overlap this very fast, but we always, for this be successful, we look for composition that has interval, a window, process window between glass transition and crystallization large enough for we proceed with the sintering crystallization.
Okay.
There's some
Oh,
guys there.
now, well, we can take one more question, and I think it was you. Yeah.
I'm sorry, in the coffee break.
Hi, good morning. I'm Marcelo. Thank you very much for the question. Marcelo from Schotten, Federal University of São Carlos. My question is regarding one of the first slides. There was like advantage of the process and everything. It was saying like can be watched, it can be observed at room temperature. What is specifically that can be? Because sinteria, I can imagine it.
Forming. You can make a tile or slip casting or extrude, 3D printing, tape casting, forming at room temperature. And then you have the green compact that you have to heat treat for sintering and crystallization. And one thing that I didn't mention that is very, very difficult is the binding. Remove the binders, especially for our additive manufacturers, is challenging. Okay.
Thank you.
Yeah.
Okay, further questions during the break. Please thank the speaker again.
Thank you.
And we are going to the second talk today, electrical properties of glasses, a talk being delivered by Professor Ana Candida Martins Rodriguez from UFSCar.
So, good morning, everyone. It's a pleasure for me to be here. So, I will introduce some different talk now about transport in glasses, ionic and electronic transport in glass. But I have seen in the posters and also in the fire talk that some of you have talked about mobility and transport properties. So, I believe I will reach some of you with my talk. So, electrical properties of glasses. This is a very important subject indeed. So, my presentation, I will do some motivation to study electrical properties of glass, basic concept, ionic conductivity, the dependence on composition, dependence on temperature, and also I will talk a little bit about electronic conductivity. So, but why to study the electrical properties of glass? Are glass insulating material? So the common sense says that glass are insulating material. Yes, they are, but they may have some properties like ionic conductivity. And the application of the ionic conductive glass, the most spread application is for solid electrolyte in solid-state batteries. So we know that electric car now are a reality. It's growing up in China, in USA, here in Brazil also it's starting. And the scientific community believes that the future of the battery will be a solid state battery. And glass can be applied here as the solid electrolyte to avoid the linkages of the battery or the dendrites grow. So the advantage of the solid battery it's that they are an ionic glass may be ionic conductive, so they do not have electronic conduction. A solid electrolyte must not present electronic conduction. If a solid electrolyte is electronic, so the electron will flow not from the external circuit, it will flow from the anode to the cathode, and then it will short circuit your battery. So we have also electronic conductive glass can be applied in screen electronic glass and thin films photovoltaics. You know these electrochromic windows, they have a layer of indium tin oxide. Okay, electronic glass are mainly coated glass. The property comes from the coating, that's true. And we have also mixed ionic electronic conductive glass. They can be applied as cathode material in solid state batteries. This is just to play. I have the cathode material we'll talk about. This is just to draw attention here that the electrical conductivity is a very particular property. For the whole material, it can spread from 10 to minus 15 to 10 to 6 for metals. This is for insulate, so it can spread 21 orders of magnitude for the same properties. So this is quite interesting. This is quite, this is a characteristic. No other properties spread in so many orders of magnitude. So what is electrical conductivity? Electrical conductivity is the answer of a solid to an applied electric field. Okay. It's the result of the directional motion of charge carriers when an electric field is applied. Electrical conductivity of a solid depends on the nature of the charge carrier. It can be electrons or ions, the density of those charge carriers, and the mobility of those charge carriers. The mobility is the velocity, the speed against the electrical field divided by the speed. So then mu is the voltage divided by the electrical field, and then we have here the general expression for electrical conductivity for all solid materials. This is very interesting. It can be insulating, can be semiconductor, or can be a conductor. This is the general expression for all solid, for all materials. So the conductivity depends on the density of charge carrier and its mobility. So in metals, let's just have a look here. In metals, electrons are the charge carriers. They are small, they are weakly bounded, they are in high concentration and high mobility, so metals present high electrical conductivity. In ionic solids, the motion of the charge carriers which are moving is an ion. An ion is a big particle compared to an electron. The ion movement is difficult because of this ion movement is difficult and slow. The density of mobile ions in a solid, in a glass, are normally small. The mobility is also small. Then ionic solids normally present low electrical conductivity. So for all solids, our conductivity is the product of N, Q, and mu. Okay, and for ionic solids, we have Z here, it's the ion valence, and the conductivity will be the sum of all ionic species moving, of all density and mobility for all ionic species. Just a brief historical here from electrical conductivity in glass. This glass was first selected for its insulating capacity in telegraph communication, let's say around 1245. But in 1285, a very classical work of Warburg demonstrated the transport of sodium ions in a glass bulb. He made a very nice experiment with molten sodium in both sides, and he demonstrated that this glass tube may transport sodium ions. Also, the zero depression in glass thermometer for ancient shot, is related to the presence of sodium and potassium in the glass. So there is, it also demonstrates the mobility of ions in the glass. In the year 70, the lithium ionic conductivity, in the year 70, there was a first boom of electrical vehicle, of searching for solid electrolyte, but it has not been successful. The growth of batteries is just after 2100. Okay, and today we must say that the mixed alkali effect, mixed former effect, and the dependence on ionic conductivity on the alkali concentration, this simple problem are still a challenging issue. We will see that when I double the ionic concentration from alkali concentration, the ionic conductivity may change for 10 times, 100 times. This is still a challenging subject. So then glass they can be extra insulant. Pure silica is extra insulant because here, pure silica, there is no free electron, there is no ionic, no free ion, so it is truly insulant. Okay? Pure phosphorus, pure P2O3, so former glass with only form are truly insulant. But if you add to the glass former, you add one glass modifier, which can be an alkali oxide or a silver. Silver is a good modifier, and silver will lead to high ionic conductivity. So the ionic bonds here, our modifier will break these ionic bonds, and you introduce break the covalent bonds, sorry, and introduce ionic bonds, and then those M+, those ions, those alkali ions may move, because this is an ionic bond. They can move if I apply an electrical field through the glass. So most representative mobile ions: lithium, sodium, potassium, and silver. Silver is also a mobile ions in glass. That's also quite surprising, because if you think in the ion size, silver has a much bigger ion size than lithium or sodium. There are also ionic conductivity by divalent cations, although those are really much bigger than alkali cation, but it has been demonstrated that lead, for instance, can move in a lead silicate glass. So this is again the same picture, just to show you that this alkali ion will be bonded with an ionic bond to a non-bridging oxygen, and this ionic cation may move from one bridging oxygen to another one. Ionic conductor, so this is I already, when we add a modifier I to the ionic conductor, it can be conductive. So this will be an ionic conductive glass. And this is the same image. So I have my glass network, I add some sodium oxide, I break those bonds, I introduce non-bridging oxygen. The same could be taught here in a phosphate glass. So I introduce non-bridging oxygen, and because of that, this sodium, in this case, this sodium may move in the glass structure. So, but glass may also be electronic conductor. If I have a glass former plus a transition metal, to be an electronic conductor, I must have a transition metal in the glass, because the electron will move from a lower oxidation number to it will move from a metal with a lower oxidation move, and they will move by what we call the small polaron. So, but we need to have this transition metal with different oxidation numbers. If all of them would be, this never happen, but if all of them has the same oxidation number, so we cannot have this jump. So, and if I have here, vanadium is a very good example to introduce electronic conductivity in glass. Iron is another good example. So if we have a glass with a transition metal and with an alkali modifier or a silver, this glass here is a pure electronic because the electron moves from vanadium 4 to vanadium plus. This glass here is a pure ionic, and we can have this glass, silver oxide, vanadium oxide. And if you have this system, we will have a mixed ionic electronic conductivity. So this here, if you have silver and vanadium, this is a good example of, this is P2O5, sorry, this is P2O5, not vanadium. This, we can have a mixed ionic electronic conductivity. And mixed ionic electronic conductivity is very useful. It has been much more, very studied, researched for cathode material. So the cathode material for electrochemical device, they must have an electronic conductivity because they must accept an electron, but they must also accept an ion to be introduced. So the cathode material here, we can receive an electron and can host an ion and then deliver this ion. So, and this is an example of this family, this series of glass. We can make the whole series. And so here in the vanadium-rich size, it will be most electronic. So the electronic conductivity will predominate. And here in the silver-rich size, we can have the ionic conductivity will predominate. So, how to determine the electronic or ionic conductivity? This is a very challenging subject. This is really, it's not easy. There is not a method which is truly feasible. There is, I will talk about two potential methods. We have which is called the Wagner method. We have a blocking electrode, our solid electrolyte, and another blocking electrode. For instance, if I have a lithium conductor here, let's say lithium disilicate, which is pure lithium conductor, and with golden, a layer of gold deposited in both sides. So the golden, this electrode will block lithium ions, and after a certain time, the lithiums will be blocked if I apply a DC potential, a direct current, and then the current drops because of the blocking electrode. If I still observe a current, this current will be proportional to the electronic current, and I can calculate the electronic conductivity. But the problem of this method is that the electrodes are never 100% blocking. So sometimes there is an error associated with those electrode which is not really blocking. There is another method. There is not only those ones, there are more methods, but for instance, this is the electromotive force method. If you take a cell, if you take here, you put your solid electrolyte between two electrodes, two different metal electrodes, there will be an electromotive force between them. So, and if you measure electromotive force with your solid electrolyte, if the solid electrolyte is purely ionic conductive, the experimental electromotive force that you will measure with a millivoltmeter will be equal to the theoretical one. So then the electronic transport number will be 0. So this is, if experimental and theoretical are equal, the electrical transport will be 0. But if you have some electron moving in your electrolyte, you will measure an experimental electromotive force a little bit lower than the theoretical one, because you will have some electron moving from in the electrolyte. And this will make what you are measuring lower than the theoretical one, and you can, with this, calculate the electronic transport mover. This is a much more sophisticated method than the Wagner's methods, because you must have a reliable cell. So you must know, you must choose, your cell will be composed for two metals, different metals, otherwise you will not have an electromotive force, but you must know exactly or precisely the theoretical electromotive force of your cell. So, then glass are good candidates for solid electrolyte. Why? Why? Because if it is an ionic glass, a classical ionic glass, lithium disilicate, sodium disilicate, so they have no electronic conductivity or negligible electronic conductivity. It's 10 to minus 9. So it will be okay to be used as solid electrolyte. They also have no anionic conductivity. That is nice. So sometimes some cells have some polymers as solid electrolyte, and the polymers sometimes may have ionic mobility. So this does not happen in the glass. So then the ionic transport number is very close to 1, which is nice. Glass have good chemical stability. We may vary with variable composition, but there is one drawback. I don't know if it's written here. One drawback is that the conductivity of a normal glass, what I call normal glass, with a modifier, classical modifier former glass, are not that high. But if you go, for instance, to sulfide glass, this is a glass. If you go to sulfide glass are almost as conductive than this is beta alumina, which is very well known. It's a crystalline solid conductor. So you see that glass here may be well located for ionic conductivity, but those are sulfide glass. Oxide glass has much lower ionic conductivity. So those are typical numbers for ionic conductivity. If normally glass are more conductive than the isochemical crystal, because in crystalline material you have always the same barrier, the same activation energy to be surpassed, and in glass you can have this lower barrier in the activation energy. So if you take, for instance, the lithium disilicate glass at 100 degrees, the glass has 10 to minus 4, the conductivity, and the crystal is 10 to minus 8. So the glass is much more conductive than the isochemical crystal. And here we have an activation energy of 0.64, which is a high activation energy for an application. but the crystal has much higher, even much higher activation energy. We have few examples of isochemical glasses, but if you take the niobium, lithium niobate, it has been obtained as glass by hyperquenching, by roller quenching, and so we have a 0.44 activation energy, and we can compare with the polycrystalline one, which has a much higher activation energy. It's true that the lithium niobate, depending on the atmosphere, may be ionic conductor or electronic conductor. So this is an exception of the glass, of the general rule. This is what we call Nazicon glass. So this is a glass composition which, when it crystallizes, it will crystallize in this very special crystalline structure. So, and because of that, in this case, the glass has a conductivity much lower than the crystalline one. But this is because the Nazicon structure has this open channel, and they have the sodium or lithium, they are located in very special place. So because they have those open channel, they can move with very low activation energy. So then here in this case, the crystal is much more conductive than the glass. Because if you calculate here, this glass does not have a high concentration of lithium, and because of this very special structure, the crystal is much more conductive than the glass ceramic. All of those are glass ceramics. This again, this is a table to show the lithium conductor and oxide glass. The more conductive oxide glass that we found in literature is this one with niobium, is a niobium phosphate glass with a high amount of lithium. So which a conductivity at room temperature 10 to minus 6 and an activation energy 0.58. For oxide glass, this is our record up to now. So electrical conductivity of glass are strongly dependent on composition. We have several effects. We have the alkali concentration. So we see here that the conductivity rises exponentially with the alkali concentration. We have what we call the halogenated salt, or the dopant concentration. We have the mixed alkali effect and the mixed former effect. I will talk a little bit about all those effects here. For instance, this is the alkali modifier concentration, and this is very challenging because people talk a lot about the alkali modifier and mixed former effect, but this is also very challenging to explain why, when I increase from this is 5, this is 10 mole soda of sodium oxide, is a pure silica soda lime glass, why the conductivity increased by 2 orders of magnitudes or more. So this is still challenging to be explained. Again, because there is no, if you take the expression of the mobility, if you take the expression of the mobility, I don't have it here, that there is no term in the mobility which would explain a so huge variation. The mobility depends on the frequency, on the lambda distance, kT, and electronic charge. So it is really not very explained that the main distance will change 2 orders of magnitudes in the glass. So to explain that, Raven and Souquet proposed in the 70s that glass would be a solution in which the glass forms the solvent and the glass modifies the solute. Let's see in the case of water. Let's compare to the case of water. For instance, in the case of water, the resistivity of pure water is very, very high, 18.2 megaohms. which means that a conductivity is 10 to minus 8, 5 to 5, 10 to minus 8. So, but if you put a little bit of salt in water, for instance, KCl solution 0.01 molar, the conductivity increase from 10 to minus 8 to 10 to minus 3. So with just a little bit of KCl, the conductivity of water increases 5 orders of magnitude. That's the same. We could apply the same reasoning to our glass. If you still increase 10 times here, so here you see an increase of still 1 order of magnitude. If you have 1 molar KCl solution, then your conductivity will be 10 to minus 1. So the same thing we can imagine in the glass. So Haveni Suke proposed that the alkali like lithium oxide, sodium oxide, is weakly dissociated in the glass matrix. So there would be those species, dissociated species, and undissociated species. My point is really challenging me. So, and because of this, we can imagine an equilibrium dissociation. This equilibrium dissociation would be can be described by the activity of both dissociated and non-dissociated glass. The activity is equal the concentration multiplied by the coefficient of activity. So, but the conclusion of this is not all M+, not all alkali, not all M+ are effective charge carrier. So only some of them will contribute to the ionic conduction in the glass. If N+ is the concentration of effective charge carrier, we can write this N+ would be proportional to this equilibrium dissociation, to the equilibrium dissociation of the dissociation I have shown, and to the activity of M2O. And then the conductivity would be proportional to this activity and a constant. This can be derived from thermodynamic equation. It's not that simple to arrive here, but it's simple thermodynamics. Then Haveni and Suke, what they did, they measured the activity of 2 different glasses with different sodium concentration. And they plotted that sigma of those 2 concentrations as a function of the activity of the alkali is proportional. So they have found here a straight line with different, those are different glasses. So they made a concentration cell between 2 different glasses with 2 different concentrations of alkali. And this makes a concentration cell, and they can measure the electromotive force. Okay? And they found that this good correlation between conductivity and the activation energy. Those experiments have never been repeated. This is a very nice work to be done to repeat those experiments in other glass. So because I know, I studied in Grenoble with Suke and Haveni, I knew both of them. I know they have made a very, very careful experiment. So they had three cells in the same oven, and only when 2 of them have the same electromotive force, they were measuring the same property, they will consider these results, and if the third one has not the same result, they will discard it. So, ionic conductivity of glass, we have here the nature of the alkali ions. We can see that here for the borate, that lithium is much more, has a higher conductivity than sodium and than potassium. And here, if you compare oxides versus sulfides, you see for the same formulas, you see that sulfide glass are have much higher conductivity than oxide glass. And this may be understood because sulfide glass has higher dielectric constant, and because sulfide glass has higher dielectric constant, the equilibrium of this dissociation is much higher. So we will have much higher N+ species than in oxide glasses. This is the mixed alkali effect. This is an old picture, but I like it because here we have the inverse of log conductivity. Because of that, it's showing a peak. Normally, it shows a deep depression. But I like this figure, although it is old, because it shows both. It shows the three couples: lithium-sodium, sodium-potassium, and potassium-lithium. And you can see that the mixed alkali effect is much more pronounced in the case of potassium-lithium than sodium-potassium, lithium-potassium. They explain it by showing that if the difference between both ionic radio, the mixed alkali effect increases with the increase of the difference in ionic radio. So sodium-lithium, potassium-lithium has a much higher difference in the ionic radius, then it shows a more pronounced mixed alkali effect. And this is a universal effect. So we do not know any case of mixing alkali, or even you can mix with silver, that has shown a positive effect. And the most accepted explanation of this up to now is that when you have your glass, you frozen like a specific side for potassium and a specific side for sodium, let's see. And when you want to move, so this, the sodium does not fit in the potassium side, or the potassium does not fit in the sodium side, and that's why the conductivity decreases so much. It's really striking. And or we can see there is also another theory that says that there is a pair, so a pair sodium-lithium which cannot move very fast in the gas or very easily. Or of course, when the conductivity increases, the activation energy will. If the conductivity decreases, the activation energy increases. That's also a nice feature. So if you let's see the doping salt effect. Let's have a look to this glass here. This is a very interesting system, glass system. If you take silver iodide and silver phosphate glass, if you add silver iodide to silver phosphate glass, the mole number of silver does not change. So we have here from x equal to 0 to x equal to 1. We cannot have x equal to 1. It will not form a glass. But if you change x from 0 to 0.5, the mole percent of silver will not change. But despite of that, we have a change here of 5 orders of magnitude. When you change from 0, there is not the 0, there are GPO3. Yes, we have 0 here. The silver phosphate glass. It increases, the conductivity may increase 5 orders of magnitude. Even the molar number of silver does not change. This is a very, very nice example of the effect of this doping salt. So, and why it helps, it has not been explained a lot also, but it seems that the iodate or all allied will remain outside the phosphate chain. This has been proved already, and this creates more free volume, or maybe this lower the bond energy between silver and the phosphate chain. Because of the presence of iodine, we will have a more mobile silver ion. So it will be, the bonding energy to the structure will be lower, and then the silver may move more easily. Okay, this is another example of the allied salt. So if you add to this is a borophosphate glass, if you add halides, lithium fluoride, lithium chloride, lithium bromide, you see that we have an increase in lithium, in the ionic conductivity higher than if you have here, I wrote lithium oxide, if I added lithium in the form of lithium oxide. If I just add lithium oxide here, so the increase in ionic conductivity will be lower than if I add lithium chloride or lithium bromide in my glass. So, the influence of temperature. How does the ionic conductivity behave with temperature? Below Tg, we have an Arrhenius behavior, Arrhenius expression, and above Tg, we have like a VTF expression. So we have a kink here in Tg, okay? And this is also very classical. We have a change in the mechanism of ionic conductivity below and above Tg. And because of this is a real case, potassium silicate and sodium silicate, it's very hard to measure here near Tg. The method of measuring is also change a lot. So below Tg, we employ impedance spectroscopy. Here we must employ some other methods. That's what we do not have so many data in conductivity above Tg. But below Tg, the ionic conductivity follows an Arrhenius expression, and above we will have a free volume which may influence the ionic conductivity, and this expression is like T minus T0, it's like the VFT expression for viscosity. Okay? This is, we have very, very few examples of the whole measurement. That's why this is also an old figure. It is written as resistivity, but you can see the kink here at Tg. So there is a kink here, clear kink. The electronic conductivity, so I will just some words. The electronic conductivity is described by a small polaron. A small polaron is the movement of the electron through the chain, the macromolecular chain of the glass, and it moves. It's the entire electron, the entire cloud, electron cloud which is moving. And it is described by the Mott equation. So the Mott equation, you can see here that we have a minimum in resistivity, so a maximum in conductivity. When I have 50%, this is iron 3, iron 2 plus. And the Mott equation, we have we have the phonon frequency, the number of transition metal ions, elementary share, the mean distance between a vanadium, in case of vanadium, and acceptor level. This is the molar ratio of reduced transition metal ions, the activation energy for hoping, and we have here the tunneling factor. So we can calculate this tunneling factor. The Mott equation is which describe, sometimes we have an exponent here, 1 to 4, because the activation energy at lower temperature, there is not only one activation energy. We see a change in activation energy. So Mott has been awarded with the Nobel Prize. I don't know exactly if it was for his work on electronic conductivity of glass. And let's see something about the effective. Let's try to calculate this effective number of charge carrier and from ionic conductivity and from the thermodynamic activity. So if you take this kink here, you can see that below Tg you have an Arrhenius expression. Above Tg you have this VTF expression, T minus T0. An activation energy is the sum of the free energy. It's a free energy, an activation energy, which it can be divided by an enthalpy, and entropy, so delta G equal enthalpy plus T delta S. And the activation energy may be divided by a term of the formation of the charge carrier and the migration of the charge carrier. Then at the increase, we have a continuity in charge carrier formation, but a discontinuity in the migration mechanism. Because of that, if you plot such a graph, this was being worked in collaboration with Marcio, who is here. So we have here, we can have the activation energy from experimental. So we measure our glass and we have the activation energy. Then if we fit here the VTF expression above TG, we can have B delta H, we can have by fitting parameter. We can assume that T0 is 3/4 of TG. This is an accepted value. And so if we have B, T0, and delta HF by fitting parameters, we can go back to the experimental activation energy. Oh God, my pointer. And you can calculate this enthalpy of migration, of formation, sorry. So the N plus will be equal to this enthalpy of formation, and you can calculate the enthalpy of formation using this kind of calculation. So this is what we have done in our article. So let's see our results, and those were calculated effective number of charge carrier. So this is the effective number of charge carrier. We calculate the total number of charge carrier by density, and we can calculate this effective number of charge carrier. We see that our result shows for lithium disilicate, sodium disilicate, and potassium disilicate, we show rather a low 10 to minus 8 at room temperature. We show rather a low effective number of charge carrier, 5 minutes. Thank you, Helmut. And well, I have applied some other methods by measuring the capacitance of the electrode, and we do not have exactly the same results. But okay, those are calculated methods. So again, our silver iodide, silver phosphate, from conductivity fit above, so from density data, and we can have, and if we take, if you have the N plus number calculated, and we take this expression, and if you take the mobility, you will see that the mobility is almost constant with the composition of your glass. The mobility of the ionic, the mobility of an electron may be easily measured by ionic Hall effect, but the mobility of an ion, it's not easily measured by ionic Hall effect because the mobility is very low, and it is it's in the same order of the noise of the measurement of the ion. That's why we have very few results in the mobility, in the ionic mobility measured by Hall effect. One of these results was here, but so here we see that the change in conductivity is more due to the change in this effective number of charge carrier than in the mobility. Okay, here we have done another with Caio Bragato, most of you know from Alfred University now. This was the PhD thesis from Caio Bragato. We see that if we measure the conductivity function of log of silver iodide, he measured the activity of silver iodide. We also find a very straight line which allows us to say that the conductivity is proportional to the activity of the silver iodide. So, just few words, I do not have time. How do we measure the ionic conductivity? I suppose some of you know the impedance spectroscopy. We apply an alternative current with variable frequency, and we got this kind of semicircle, which is called the Nyquist plot. Let me see. But why using impedance spectroscopy? Who those have already used this method? Do you know why we use impedance spectroscopy? Why we must apply variable frequency and alternative current? Sorry? Because of? Barrier. Which barrier? Barrier. I think you are in the right direction, but let me, if you want to say this, because if we apply, this is direct current, the Ohm's law, if you apply here to an ionic conduct, yes, you are right, you said right. The ions will move through the ionic conductor, but the ions will not move through this wire, which are metallic wire. So the ions will be piled up in the interface, in the electrode, and this, so what you measure effectively, if you apply Ohm's law, you will measure the potential plus, you will measure the ionic, your Re plus all resistance plus electrode polarization plus over potential plus so. You will measure this potential here. You are measure much more phenomena than simply the resistance of your sample. So the contact resistance between electrolyte and cathode, and with alternative frequencies, you can measure, you can separate the bulk sample from the electrode phenomena. Okay, that's it. Thank you very much. This is an old photograph, but thank you very much for your attention. And if you have some questions.
Yeah, thank you very much, Diana, for this great overview. And now we are ready for questions.
Aleksander Szpakiewicz-Szatan, Institute of High Pressure Physics, Polish Academy of Sciences. Thank you for a fascinating lecture. I actually have a small question when you mentioned phonon hopping, because I remember one of my reviewers actually asked me about this. In glass, do we really have phonons?
Yes. Yes.
I remember. Okay.
We have glass with high phonon energy, high and low phonon energy.
Okay, okay.
Yes,
Yes. I'm asking because I remember that my reviewer mentioned that phonons were only in long-ordered structures, so in glass there should be named something like vibrational modes. That way.
You are right, but yes, in optical glasses, they talk about low phonon energy glass, high phonon energy glass.
Okay, thank you. I'll take a read into this.
I think it's more colloquial term applied to glasses, yes. More questions?
Thanks for your nice talk. My question is, if my glass has some pore structure and the nanometer scale, how this pore structure influence on the ionic mobility and the conductivity of the glass?
Sorry, if your glass has, I didn't get.
Okay, so if my glass has a nanopores structure, and how this some porosity influence on influence on the ionic mobility and the conductivity of the glass.
It can affect the conductivity, sure, it can affect, it cannot. Depending on your pore size, theoretically it will affect, it will lower the conductivity. But I have seen in crystalline structure, in glass ceramics, which we have porous, sometimes the porous does not affect that much. But theoretically, you can think that, yes, ion is coming here and it will not go through the porous. Then, yes, it will lower the ionic conductivity.
Hi, Marcelo from the Federal University of São Carlos. Thank you very much for the presentation. I was wondering, for example, in viscosity, when we measure below TG, we have a method. Above TG, we have another method. But in conductivity, below TG, I can imagine the impedance measurement.
Yes.
But how do we measure conductivity above TG?
Yeah, it's another method, completely different. You must think that it is a liquid. So normally you drop 2 electrodes in the liquid melt, and you must have you must measure very well the distance between these 2 electrodes, and it must not change. So, and you apply frequency, and you will see at which frequency you will see an evolution with the frequency. So I know also in Iena, who is in Iena here, they had a double cylinder method. It was a very special method. I hope this method is still there. You have a cylinder inside another, and they would pull the cylinder. So by moving the inner cylinder, they maintain something constant, and they can have this. But it is also with alternative current. It is also with alternative current.
Thank you very much.
Okay.
I don't know enough to ask a question, so I just wanted to make a comment. On the weak electrolyte effect, if you probably didn't notice, for the one of the data points was Pyrex. Now, for the older, more experienced people, that, of course, means Corning 7740 glass. And so they could put that in the caption that it was Pyrex. Today, you can't do that because there are many compositions of, quote, Pyrex, and so you have to be careful. They probably should have put 7740 glass, but at that time, everybody knew that Pyrex was Corning 7740. That was for the younger students to realize Pyrex is not Pyrex is not Pyrex.
Okay, thank you, thank you.
Yes, one more.
Hi, I'm Rachel from Washington, D.C. Thank you again for your talk. I was wondering if you could explain again what's the advantage of mixing the ions and the alkalides and the transition metals in glass. Is it to tune the electric conductivity and ionic conductivity? Because to me it seems like they would interact with each other, and if they're both together, then they would reduce the conductivity.
No, I didn't get the question, sorry.
Why design glasses that have mixed alkali? What is the motivation behind it?
There is one accepted model theory, is that when you have your glass, so you freeze it, so you can imagine there is a site for lithium and a site for sodium. And lithium cannot go to this sodium site, and sodium cannot go to this lithium site, because it perfectly matches. They have different ionic size, the sites. So this is one accepted theory. But indeed, in my opinion, it has not has been fully explained. And another theory is that they form pairs, and the pairs cannot move. But why would they form pairs? I don't know.
Well, actually, to complement the answer, so the main driving force has been a lot the fundamental science, because if you understand the depression of the ionic conductivity in a mixed alkali glass, it teaches you a lot about where the ions are and what are the environments of the ions are. And the current vision is that the unlike ions are more or less statistically distributed, but because of the proximity, but each one has its own individual site. And the forward-backward correlated hopping, which is unproductive for ion movement, is then favored because of the mismatch between the sites. Yeah. Actually, on top of this, I have a comment also. The distinction between ionic conductivity and mobility, electrical conductivity and ionic mobility. Insights you get from NMR, because that is element specific and tells you which of the ions actually contributes most, and also if the trends in electrical conductivity match the trends in mobility of the ions. Yeah.
Yes, Elmo, this is a good discussion also. I should include in my presentation, I always want to include, we can measure the activation energy for ionic conduction by NMR. I know it by okay, and it doesn't not match the ionic conductivity activation energy, but this may be a question of time. So in NMR you get shorter times of measurement, and ionic conductivity you have the ion moving in much larger scale than in NMR.
Right. Okay, the last questions before the coffee break.
Hello, good morning. The best presentation, Prof. I have a philosophy question for you. If the professor had to imagination the future of research in ionic conductors, what would it be like?
How can I imagine the future? Oh, it's a bright future. So we are developing now, I think you know, in Lamava glass with chlorine, for instance, and I think we can increase ionic conductivity with allied ions. Ricardo is working with increasing conductivity by relaxing time, or by changing the glass structure only by relaxing. So, did you ask it in batteries or is in applied? Did you ask for application or for science? For science, I see there is a bright future, because the mechanisms are really not so well understood. So there are lots of things to do. For the application, I believe there have been developed some glassy electrolyte. There is a very recent paper by Yuan and Yu, which joined a glassy electrode and a glass ceramic electrolyte. So, and this is nice, because if you join glassy to glassy, we have no electrode, no interface problem. So we have less interface problem than if you join metal with crystal and so on. Okay.
Okay, so we're off for a coffee break now. Let's thank Anna again for a wonderful talk. And please be back in 15 minutes sharp. Thank you.
Alô? Ei, som. Ah.
Tá. Então vamos prender. Legal.
All right, welcome back to the second morning session. The third talk of today's workshop will be given by Professor Francisco Cervena from the State University of Ponta Grossa in the state of Paraná. And he will be talking about mechanical properties of glass ceramics. Francisco.
Okay. I will use the microphone here. Hello. Okay. First, I'd like to thank the organizers of the school for the invitation to come here and participate from this wonderful week, and also to give my presentation. So my talk will be mechanical properties of glass ceramics. Just a minute. When is half an hour? Could you just half an hour, and 10 minutes? So, okay, thank you. So a brief outline of my talk will be some introduction, why study mechanical properties, then a few properties that are important for the mechanical characterization, such as elastic modulus, hardness, residual stress, microcracking, mechanical strength, and fracture toughness. So glass ceramics was discovered by Stuckey in Corning, and one of the properties he observed was that glass ceramics has better mechanical properties than glass. So usually glass ceramics is, if you want apply your glass for some mechanical application, if you can have a glass ceramic, you'll be better strength and better properties. So, as you know, has been already talking here, glass ceramic is when you have a controlled crystallization of glasses. And therefore, you can control the microstructure. But then remains some questions that I always interest in answering and studying it. For example, what are the toughening mechanisms in glass ceramics? So why they are tougher than glass? How the microstructures affect the mechanical properties, such as crystallized volume fraction, crystal size, shape, residual stresses. And can we modulate or predict it quantitatively? So when you start deforming, if you get a body and apply some normal stress, your body will deform. So if you divide the force by area, you have stress. And if you divide how much the elongation of the material by its initial length, you have a strain. And also, as you strain the material along the direction of the force, you have contraction, perpendicular. So the ratio of this contraction by the elongation gives you Poisson's ratio. And also, you can have the force applied normal to the surface, and you have a normal stress, but your force can be parallel to your surface. So you have a shear stress. And so you can use this quantity, let's say the tangent of this angle, and you can define a shear strain. Solids for small deformations obey the Hooke's law. So you can have a relation between the normal stress and normal strain, and then this constant is elastic modulus. And then you can have a shear stress and shear strain, and then you have your shear modulus. There are other constants, elastic constants, that you can describe your glass or your glass materials, but for isotropic and homogeneous materials, if you know two of them, you can know all of the others, okay? So there is a dependence. So as far as you know two elastic constants, you can know the others. So how to measure it? Okay, one way is you can do like 3-point bending, 4-point bending. 3-point bending because you have 3 points where you apply the force, or 4-1. And then if you use a strain gauge and you calculate, you estimate the stress and strain, you can, from the inclination of the curve, you can estimate your Young modulus. You can also resonate. You see if you apply or support your sample in some special points, when you touch, you produce some vibration in your sample, it will flex or it will make torsional movements. And this is related, you can hear it, let's say putting like that with a microphone or so. So you measure the amplitude of the vibration of your samples, and then if you do a Fourier transform, you find the frequencies, natural frequencies of vibration. And taking into account these frequencies and the specimen dimensions, you can calculate these frequencies are related to the elastic constants of your body. Okay? This is one way of measuring. The other way of measuring is essentially if you have your sample here and you can use a transducer to produce an elastic pulse. This pulse will travel along your sample, will be reflected in back phase, come back, and then you get the signal. So if you use an oscilloscope, you can measure the time of travel. So you know the distance, you can estimate the speed of the pulse in your sample. So you have a longitudinal wave and you have a transversal wave, and these are related to the shear modulus and elastic modulus, and then you can also measure it, the elastic constants. This is another method, okay? So if you look for the glasses, Young modulus, okay, it scales more or less from 20 microns, let's say, 20 gigapascals up to 160 for oxynitrides. So if you see, more or less, it scales with glass transition temperature. So and if you look for Poisson's ratio, glasses that has a more open structure, they have a lower Poisson's ratio. Silica, for example, is 0.15. And as you polymerize, you have a more dense structure, as shown here, your Young modulus increases, okay? And if you look for glass ceramics, the elastic modulus is usually higher. So if you look for glass ceramics or lithium, magnesium, silica, you see the range here is around from 80 up to 120, maybe higher a little bit for gunite. So usually glass ceramics has higher Young modulus than glasses. And there has been some work by us and also by Professor Zanotto's group. Oscar is here, was part of his work. And it was measured how the elastic modulus varies as a function of crystalline volume fraction. So you see that in a biosilicate glass, you have an increase that is almost linear, as well as for lithium disilicate. In both of these experiments, the crystal size was kept constant. So we have the shape and the size of the crystals kept constant. The only variable here was the crystalline volume fraction. So you see that there is increase on the glass from the glass to the glass ceramics, and also for the lithium disilicate. The other property that is important when you talk about mechanical properties is hardness. Hardness, essentially, there is, well, we can say that is a material resistance to penetration or to elastic plastic deformation. We'll have an excellent talk today at 5 o'clock by Professor Yoshida. He is a very famous and one of the persons that know most about indentation. So hardness is has many advantages. It's a simple, cheap, fast technique. you need the preparation of the sample is very simple, it's non-destructive, you can probe very small areas, and also under control conditions, you can possibly estimate yield stress, creep exponents, and so on. However, hardness is not a material property. It depends on the type of the indenter, depends on the technique that you use, maybe the load. So you cannot get a hardness and say, this is a material property, okay? You should, when we say a hardness, or when you look at hardness value, you should look for what kind of type of hardness was made, and what type of the indenter, what type of load, how many indentations were performed, what are the conditions, if fast, if slow. So all of these will affect your results. But however, hardness is a very important property in several other properties that we look for. For example, abrasion, wear, erosion, contact damage. All of these are important. We see that harder materials are more abrasion resistant, wear resistant, and so on. So this is a very simple technique that I show you for Vickers hardness. So you have like a square-based pyramid, usually made of hard metal like diamond, and then you press gently over the surface, usually for people who are not used to mechanical properties. When you say, oh, hardness is you press an indenter on the surface, people think that you just poke the sample. It's not. You press gently, okay? This is made slowly. You must make the application of the load in a controlled manner. So when you look at the microscope, you see this square, and if you measure these diagonals, you get a measure of the hardness if you know the load as well. And also if you have a glass, you have these radial cracks. And also you have here Vickers, but you have Knoop and Brinell, other geometries, okay, for a specific purpose. You also have instrumented indentation. Instrumented indentation is when you apply the load, but you control the displacement of the indenter and also the load that you apply. So you have a curve of the applied load against the penetration of the indentation. And from here, you can estimate also the hardness, and from this inclination here, the elastic modulus, okay? So you can make this equipment with some motorized X and Y, and then you can probe very small areas in the material. So this is one technique that is possible also to use to measure hardness and elastic modulus in very small volumes. This is a typical curve for a series of called Mohs scale that was I think was the first scale of hardness used for mineralogists. Mineralogists, they can go to the field, and then you get a rock, and then you gather one rock, and the idea of this scale is the higher your number in the Mohs scale, if you scratch this on that, it will scratch. For example, calcite will scratch gypsum, but gypsum will not scratch apatite. So it's a very field technique that you can carry, for example, a piece of quartz in your pocket, and then you scratch. So you see more or less where is your mineral that you find in the field. When you indent glasses, and this is also true for glass ceramics, because they have a glass matrix, when you press, you have a deformation here. And what you observe is that there are two main mechanisms. You may have densification here, where essentially you have usually a high hydrostatic pressure under the indenter. Usually 1/3 of the pressure that you apply. So if you have like 6 gigapascals of, which is the typically soda lime hardness, here you have 2 gigapascals of pressure, compression, hydrostatic. So under these conditions, those glass that have a more open structure, they condense. The microstructure, there is folding of the structures. So if you have glasses with low Poisson's ratio, okay, they densify. However, if the structure is more compact, which means higher Poisson's ratio, you have shear deformation, shown here. These two mechanisms, they are not exclusively, means it's not either one or either the other. Okay, for example, if you look for soda lime densifies also, but most of this deformation by shear. So you have both of these mechanisms operating. So here, just to show, these are the glasses hardness as a function of glass transition temperature. So you see that as you increase the transition temperature, the hardness increase. And here, the different patterns of microcracking that you have when you indent on different glasses with a different Poisson's ratio. So you start here with silica, which has a more open structure, and you go along to metallic glass, which has a more compact structure. So you see here that you have cone cracks, and then as you go up here, you have the radial cracks and lateral cracks, and maybe no deformation, only plastic deformation here. Okay? So the Poisson's ratio affect what the fracture mechanism around contact loads. And this is important because glasses that densify, they are most abrasion resistant. Let's say if you get a load and a sharp contact and you scratch your glass, if it densifies, it is a mechanism, not all exclusively one, but there is others. But this glass will be more scratch resistance. It won't produce cracks if it densifies. Okay? And machine learning has been used to predict glasses. So this is a shape from elements. So if you essentially, if you have these elements here, they contribute negatively for hardness. But if you have the alkali and strontium, zinc, barium modifiers here, you increase your hardness. Okay? So this has been also one of the properties that machine learning has been used to study the glasses. So also Oscar Pelch, Professor Pelch from Zanotto's group has done some interesting measurements on hardness, keeping the crystal size constant. So here is crystallized volume fraction, C hardness. You see that in some compositions, the glass is here, so increase a little bit, keep constants, decrease a little bit. If you look for lithium disilicate, something happened here. If you look for lithium disilicate, it increases almost linearly, also for constant crystal size. Now, looking for fracture, you can do theoretical calculations. You can do some approximations, meaning thinking, for example, you have two atoms, so as I pull this atom to this side, maybe the deformation may be a sign, and you can estimate more or less that the theoretical stress to separate this atom, which is the cohesive strength, would be a fraction of the Young modulus. Okay, would be like E over 5, E over 10, E over 8, depending how much you consider. Okay, but and here are some examples. So, for example, if we have a silica fiber, is E over 4, iron whisker, E over 23, silicone whisker, E over 26. So it's always a fraction of the Young modulus. Okay, and this is a classical work by Griffith. In the beginning of last century, he observed that if he got, this is a replot of the original, of his data, of his original paper. So he observed that if you get glass fibers, first it break at a much lower stress, E over 400, okay? But as you decrease the fiber diameter, you start reaching the limit of the theoretical strength. So why fracture strength varies with fiber diameter, okay? And he came up with his famous theory, Griffith theory, which means that he considered, imagine you have a 2D crack in a body under tension, and the mechanical energy stored there as a crack, with the crack, is given by this relation, which varies with crack length a square. But imagine that if this crack propagates, it creates surface, okay? And surface, you need energy. So it's a balance between this mechanical energy that is stored in the crystal plus the work done by the applied load. They are used for increase in the new fracture surface as the crack grows. That's why you have like 4 here, because you have 2 surfaces here. So essentially you have an equilibrium. As the crack grows, if the mechanical energy supplied is enough for the crack to create a surface, the crack will grow unstably. So you end up with this equation. So the stress for this crack to start running is given by 2 times the energy surface Young modulus divided by the crack size. So longer crack size produce lower the stress and is proportional to the energy crack surface and the elastic modulus. So Griffith was able to explain that if you have larger fiber diameters, you are allowed to have a higher probability to have a higher defect. That's why the stress falls. However, if you have less volume, the probability of having a larger defect is decreased, and then you increase your strength. Okay? So if you look at the Griffith's equation, you can know that 2 gamma is a material property, so we can call this energy release rate. And when your applied energy release rate is equal to 2 gamma, which we call critical strain energy release rate, you have a fracture criteria. Okay? So this is one of the criteria. G is equal to GC, which is based on energy criteria. But you can also rearrange that equation and put here, including the elastic modulus. So you have a material property here, and you have this term on the left here. And if you do some analysis of the stress field around the crack, you see that it always appears this term. And this term, in fact, it defines the intensity of local stress around the crack tip. So this term here is called stress intensity factor, and this term here is called critical stress intensity factor. So you have another criteria, which is the same as the other, but when your stress intensity factor equals the critical stress intensity factor, you have a fracture. Okay? And you can apply the load on 3 different ways in your crack. You may have an opening mode like this, so you open. You may have shear mode, and you have tear mode. When you have scissors that you cut papers, you are cutting in shear mode. Yeah, you get your paper and do like this. So the force applied is parallel to the crack surface. So this defines 3, which call 3 modes: mode 1, mode 2, and mode 3. Okay? Each one related to a different type of application fluid. Where is related to a crack? When you have a crack in a glass, and these cracks, for example, encounters a precipitate, it may tilt. In this case, you have mode 1, mode 2. Okay? And when a crack, for example, twists, when it encounters for something, okay, now in this case is on mode, it has mode 1 and mode 3. So essentially you have K1, K2, and K3. You have 1 K for each mode, and they are related to G along this relation here. In case you have a mixed loading, this is the criteria used for fracture. So when you look for glasses, okay, you see you have chalcogenide glasses with very low fracture toughness. It's about 0.2. And if you increase, you may have like 1.2, the silicon oxynitrides. You can relate with other properties, but the Roxel was plotted here as a function of hardness. Okay? And if you look in the literature, one technique to estimate fracture toughness has been the indentation fracture toughness. And today we call indentation fracture toughness. We don't call fracture toughness. Why? Because fracture toughness is a material property. It's not like hardness, okay? So if you look for fracture toughness is a material property. So ASTM has 3 methods to measure fracture toughness. Of course, depending on, there has been some work, maybe one of technique or the other is not appropriate for your material, but all of them, if performed properly, should have the same value, okay? However, when you do indentation fracture toughness, you are not. Depending on the method you use, depending on the indenter, you have different values, okay? So there has been, we call it indentation fracture toughness. Why indentation fracture toughness is still used? Because it's a quick way of probing. Let's say if you have 20 compositions and you want to know the probability of cracking, okay? Preparing fracture toughness, samples for fracture toughness measurements is time consuming. You need some material, you have to prepare them, you have to test them. Although the testing is quick, the preparation is labor intense. So sometimes it's easier for you to do a KC, let's call it indentation fracture toughness KC. It's usually for you to do a quick test of KC and probe what is the best, or 2 or 3 compositions that has the higher KC. So that's worth then doing K1C testing, okay? So there has been this model proposed by Youngstis in here, so it depends on the elastic module's hardness, the size of the radial crack and the load, and there is some calibration here. The another equation that has been proposed is Nihara, which we use here, and that KC is not K1C, that has been demonstrated in this famous paper by Quinn and Bratt, that they measured on certified NIST ceramic materials, that you see KC here, is Nihara, is not the same, and this is another model, does not give the same fracture toughness as you measure properly, okay? So you should be careful. When you do a KC measurement in your paper, don't write fracture toughness. Write indentation fracture toughness, okay? Because we are doing some research for a review paper, and I found several papers with fracture toughness, and we look carefully. People have measured indentation fracture toughness. There is no problem, but it's good for saying indentation fracture toughness, okay? So what about here? We did some indentation fracture toughness compared with K1C by double torsion, which is one technique, and you see that for lithium disilicate with constant crystal size, they are not the same. So another thing that is important is that crack depends on humidity, okay? Okay, that's called fatigue effect. And this is Professor Wiederhorn, that is very famous. You must cite him in all his work. And he produced this famous graph here, okay? So essentially, we have 3 regimes here when you have the crack velocity against the applied force. So you have a regime which is called regime 0, which is the threshold where below this, you don't have crack growth. Then you have a region 1, which is a stress-induced corrosion mechanism. So it's reaction control at the crack tip. It follows usually this relation here, which is this exponent n. The higher the exponent n, the higher resistance to fatigue is your glass. You have a region 2, which is a plateau, and then you have region 3 here. The region 2 is the most, well, region 0 is important because below that stress you don't have crack growth, okay? But the region 1 is the most measured. The important thing here is that your K1C is over here. So it means your crack grows below K1C. So you apply stress and your crack grows. So that's dangerous because you do a normal test and your crack size is okay. But passing the time, your crack will grow under the action of humidity, and may you have failure. So if you have more alkali in your glass, the fatigue of a glass will enhance. Okay, so essentially because you break the silicon oxygen bonds at the crack tip. Another thing that is important is that residual stress. When you have glass ceramics, you have intrinsic residual stress if you have different thermal expansion coefficient. Okay, and I'm not going to talk much in detail, but there is a Celsius model that essentially predicts the stress here in a precipitate that has a difference in thermal expansion. Delta T is Tg, a difference between Tg and room temperature. So just think that the crystal occupies a volume at Tg, and when you cool down your glass ceramic, okay, the crystal will shrink. Well, let's assume alpha is positive, okay? So it will shrink to a volume, but the glass, the empty space that occupies at Tg will shrink as well. But if you have different thermal expansions, the volumes will be different. But as they are bonded well, so they will accommodate more or less in the middle. So this will introduce stresses, okay? Can be compression, can be tensile. For a spherical precipitate, you have a stress that is homogeneous and hydrostatic inside the crystal. One important thing, the stress does not depend on crystal size. This is another misconception. People think, oh, bigger precipitates will have bigger stress. No, they don't, okay? Nano precipitates, macro precipitates, they will have the same residual stress. Okay? What will change is the energy. Bigger precipitates will have more stored energy. And under the right conditions, this energy is enough to nucleate a microcrack. Okay? So, I'm just skip this just to show that the residual stress depends also on the crystal shape. And just to show you, this is some cracks in a work by David Green. It's an old work, but very famous, I like very much. You have here some oxide, thorium oxide, I think. And here is a crack. You see that when you have your thermal expansion of your crystal higher than the matrix, if you look for the stress, okay, the crack follows this pattern here. It avoids the crystals. However, when you have a different thermal expansion, you see that the crack follows, it goes across, okay? And this is just to show the different residual stress. We published a very nice review on residual stress in glass ceramics back then, so if you wish more details, you can go there and have a look, okay? This is just to show for different systems, so you can, as I told you, bigger precipitates have higher mechanical energy. So you can work out what is the stored energy, what is the stored energy, mechanical energy stored in the crystal, in the matrix, so we can estimate more or less the size of this crack, so you can up with a critical radius for spontaneous microcracking. So this is a crack in the glass matrix, and this is a glass that was sintered. So you have crystal here, and you have a big big glass particle here that was cracked, okay? And you can detect this spontaneous microcracking. When you do like bending, you see that once you have microcracking, this is the next slide, but when you do on cooling and you do microcracking, you can hear, if you have a microphone, you can hear when this microcrack occurs. If you do dilatometer experiments, you see a hysteresis, okay? Because when you increase the temperature, your sample expands, and then when it cools down, there is friction between the fractured surface and produces this hysteresis. There is several techniques to measure residual stress, okay? So there is one work on NMR, several on X-ray diffraction. There is Raman and fluorescence spectroscopy, and also the indentation technique, okay? If you go to the review article, you'll find all of them listed in detail there. What about mechanical strength? Mechanical strength is one important property, although I don't like it very much. Why? Because it depends on how you prepare your sample, depends how you test your sample, okay? And it's not a material property. One way of measuring is for ceramics is bending, 3-point bending or 4-point bending. Usually 4-point bending will give you a lower value than 3-point bending. Essentially why? It's essentially because under 4-point bending, you have a bigger region under tensile stress here. So the probability to have a bigger flaw is higher. So the strength is lower here than there, okay? But anyway, it's an important property. People will measure, people will try, especially in the industry, what is your mechanical strength. But so bending is one way. There is the Brazilian strength testing where you compress a disc. And also there is bone three balls test. I like very much this test, although the sample volume under tension is small, but it's a good technique because it avoids the edge effects. If you have a bar, the stress tends to be concentrated along the edges of the bar. So these tests avoid that because you apply a load in one phase centrally and another you divide by 3, okay? 3 points of support. Here are some strengths of some glass ceramics. And just to mention, there is some very nice old work performed that you can tell us something about. This is a nice work where you have a strength as a function of mean free path. Mean free path means the distance in the glass matrix between two crystals, okay? So you have higher volume fractions, the crystals are closer together, so the mean free path is smaller. What this graph tells you is that you have a region of constant strength and an increasing strength, okay? Essentially what it's telling us is that if you have a critical defect size, okay? If you have spheres, your crystals are larger apart than this critical defect, you are here in this regime. Your critical defect is constant, produced by pores, whatever, and you have constant stress. But once the crystals start getting closer, your crystallized volume fraction increase, so you decrease your critical defect size. So you have an enhancement in the strength. I think the battery of my pointer finished, but let me go here. So this tells you that the microstructure controls that. Then this is just to show you in the red line. This was done some old work for 4 glasses with torial spheres with different compositions. So you change the glass matrix, so you'd have thermal expansion lower, equal, and higher. And you see that the strength here, the failure stress, is higher for when you have equal thermal expansion coefficients. So if you have different thermal expansions, either above or below, positive or negative, this will not give you a good mechanical strength, okay? I'm sorry. Okay, so these are some measurements that was performed. You see over there, you have the strength measured in the above part, and the below part, the nucleation of different phases. Okay, so if you see here, when you have lithium disilicate, you have an increase in mechanical strength, okay? So nucleation of new phases induces enhancement of mechanical strength, okay? And also you can have microcracking. So in this small, on the left, small graph here, you have a sudden drop in the toughness, and that's due because of microcracking. So your microcracking, you have microcracking, you have a huge decrease in strength, okay? This is some work of strength doing as well on biosilicate glass. So you see over there on the top right corner that the fracture, crystallized model fracture for constant crystal size, you see that the flexural strength increases and then remains constant. Here, the mechanical strength doesn't vary too much with crystal size. If you go to lithium disilicate, you see that increases, okay? And with crystallized volume fraction. I won't go into details here. So there are more literatures, more results from the literature, but the basic conclusions are glass ceramics usually have a higher strength, high internal stress, promote lower strengths, okay? And if you have, depending on the phase that you crystallize, you may have strength enhancement. Now, the last topic is fracture toughness, okay? There has been in the literature some compositions that have been known to have good mechanical properties. One of them was Cerebon, and Cerebon was attributed to have high strength fracture toughness due to crystallization of wollastonite. The second one is IPS impress, and if you compare with leucite here on the red squares, you see that if you go to IPS impress, leucite to IPS impress based on lithium disilicate, you see over there that you have a flexural strength from 100 more or less to 400, so it's a 4-time increase, and also K1C increase 3 times almost. So that was attributed for, if you look on the crystals on the right there, the lithium disilicate has this interlocked microstructure of needles, okay? So the better properties are attributed to this structure. Enstatite as well. It has clinoenstatite. It has a microstructure that produces toughness around 4.6. You have indialite as well, which has K1C around 4.3, which is pretty high for glass ceramics. This is a microstructure of it. We have also canacite. Professor Mikulski worked with this as well. So you have their fracture toughness from 3.2 up to 5, which is the highest I think you can find in glass ceramics. So we did some study on 2 model materials, lithium disilicate and biodisilicate. Why this? Because of the importance of lithium disilicate in dentistry, and most important because in the crystals they have compressive residual stresses. Biosilicate is also important, but because it has tensile thermal residual stresses in the crystal. So you could compare it, okay? So there are several toughening mechanisms that happens in glass ceramic. I'm going to skip that. There is you can look for one of the articles that explain all of them, but the residual stress may have an effect. This is a topic where we are doing research now. What is the effect of residual stress in fracture toughness? There is models that explain it should increase, but when you compare to experiments, it doesn't. So we are is doing this. For example, the fracture toughness, well, this is KC, but you see that it increases on the left. You increase with crystallized model fraction, and the dotted line, dashed line, means the prediction for the theory. So it's the opposite, okay? So it must be wrong. Something is wrong, okay? So we did that also in lithium disilicate for constant crystal size. This is Professor Mariana Villas-Boas. She changed the composition of residual glass in order to have higher, equal, and lower thermal expansion than the crystals, and see what is the effect on the mechanical properties. And the conclusion in the end, she did a lot of heat treatments, a lot of compositions, okay? So the conclusion in the end is that it does not have effect, at least in this microstructure. This is a very nice because you quantify the topography in LS2 glass ceramics, and then you could have, let's say, a frequency against the deflection angle of the fractured surface, and then you could use that as an input model to estimate how much crack diffraction and crack twist contributes to the fracture toughness, okay? So we see a lot of modules that does not explain everything on that. And we propose a very simple model relating the elastic modulus and the area essentially where you have when you have increased crystallized volume fraction. Okay, that explains very well the experimental data. So I'll finish here. Okay, just to show you, these are some crack toughening mechanisms that you observed here in LOS2. This is increasing crystallized volume fraction. If you look on top, you have a 13 crystallized volume fraction. You see here that you have crack arrest. Just on the right, on the left, you see the crack stops in a crystal over there. And then you see crack branching. And this is on the right is a photograph of the fracture surface. So you see that the crystal traps the crack as it propagates. And you can see if you look carefully, you see some bowing as well. As you increase the crystallized volume fraction, you see the white areas are the crystals, the dark areas are the glass. So you see that you have crack bridging, you have some closure, we think due to residual stress on the crack on the right, in the middle arrow. Okay? As you increase more, you see that the crack starts to propagate along the glass islands that are in the microstructure, essentially because the residual stress is tensile and high in this region. Okay? And if you increase even more, you see pores over there, but you see crack deflection, crack bridging, crack branching. Okay? So this is already published also in another paper. This has been supported by modeling where they simulating lithium disilicate and they observed what we observed experimentally. Okay? There is another systems that we have been working with. This is a dental ceramic based on metasilicate with this house of card microstructure that has excellent fracture toughness and excellent fracture strength. Okay, this is transparent nano lithium disilicate glass ceramics. We observed that decreasing the crystal size, you improve fracture strength, but you do not increase fracture toughness. Okay, this is another work of biodisilicate, but I will skip that for us to have time. And you may ask afterwards. I'll be happy to answer. Just to highlight this is the strength against crystallized volume fraction. You see that you have a decrease in strength when you have spontaneous microcracking in the microstructure. You have an increase in K1C with crystallized volume fraction. This is some, and I'll finish with this. You see, what we see here on the left is K1C against crystallized volume fraction. On red, in red is plotted the lithium disilicate. You see that if you change the residual stress, does not affect, at least in these two systems, the fracture toughness. Okay? So our hypothesis is that residual stress does not affect fracture toughness. And there is some other work here that I won't talk about. Our curve. These are conclusions. If you have a very increase your fracture toughness or material properties, increase crystallized volume fraction, look for a tougher crystallized phase. Large crystals may induce R-curve behavior, which is good because increased K1C, however, will decrease mechanical strength. Okay? There are other topics that are important that I didn't talk about, the fatigue testing, stacking dynamic, strengthening by ion exchange, tempering, indentation cracks, crack resistance, wear, and so on. So I'd like to thank a lot of people with whom I collaborated, and for the supporters. And again, thank you all for the attention.
Thank you very much, dear Francisco, for introducing us in this very comprehensively into the mechanical properties of glasses and glass ceramics. I already see a lot of hands there.
Okay.
Okay.
Voltou.
Hi, my name is Anju. I'm from Autoshot Institute of Material Research. So I would like to ask you about the Vickers indentation test that you mentioned in the presentation. So when we are working with laminated glasses and we are doing the Vickers indentation test, once what I did was that I changed the height from 5 centimeter to almost 2 meter height. I changed the Vickers indenter height. And then when I did the Weibull analysis and plotted the graph, I extrapolated the graph to more than 2 meter, until 30 meter, let's say, and I predicted the result that, okay, if it is from 5 to 2 meter, if it is like this, then until 50 meter, the fracture pattern or the crack distribution will be like this. And then my supervisor said that it's not ideal to extrapolate the graph after studying this small distance. So could you please comment on that?
Yes. I think you are talking about impact test, yes?
Yes.
Yeah, she's talking about you have a Vickers indentation with some weight, and then you drop from certain height. So essentially you have potential energy dissipated in the impact, okay? I'm sorry, but I'm not expert on impact test, which is different, you know. I usually do, as I said, control manner. We apply the load in 10 seconds, 15 seconds, and there is some work that recommend 30 seconds, okay? So we apply very, very gently. It's very important your work because its impact needs this kind of thing. What I suggest, Professor Satoshi Yoshida, he's an expert in this. His work is in AGC, and I've seen he is working with this, with impact test. So today at 5 o'clock, he'll give a talk. I don't know if it's specifically on this, but ask him. He'll know your answer, okay? Because he's working with this technique. He's improving it. He's doing instrumented impact test, which is good. So I think he's better. I'm not. I don't have so much expertise on this thing. Thank you.
Thank you so much.
So I'm afraid we cannot cut too much into the lunch break. So I can take a couple more questions. Short questions, short answers, please.
Okay.
Hi, Professor. My name is Laura. I'm from Federal University of Lavras. Thank you for your presentation. And I was wondering if there a way to link the bending test data to get more precise property, or do you feel it's not worth the effort and we should stick the other measurement techniques instead? Because the bending test is important to others materials like concrete.
Yeah.
And I was wondering if in the glass, is there a way to correlate the results?
I would say you have, I think, well, let me explain like this. It's not because I don't, perhaps I said I don't like it's too strong, okay? Perhaps I would say I don't prefer, okay? Why? Because if you do a lot of testing using, for example, bending, you may have Weibull modulus. And this is hugely important, you know? If you have a high, in terms of companies, okay? If you have, you know, Weibull modulus, when you do Weibull plot and then you have the Weibull modulus. So if you have a piece that you fabricated that has a low Weibull modulus and you have a high Weibull modulus, that's very, very important, okay, in terms of predicting failure. So first thing, I mean, I'm not saying it's not important, okay? Second thing, I think if you are in a way that the failure that produces the defect that produces the failure in bending is because of your microstructure, okay, from your piece, that's fine, okay? But if it's something that we introduce by bad polishing, okay, or bad sample preparation, let's say corners or something, okay, then you're not measuring something that is from your sample from your microstructure, okay? Maybe you have pores, that's important, I think that's valid. Maybe you have intrinsic microcracking, so that's important, bending as well, okay? But if you prepare bad your sample, that's any measurement, you know, if you prepare bad, then you won't give you meaningful results. I think, let me contextualize better this.
Okay.
Okay.
One more short question.
Thanks for your presentation. My name is Mariam from Trento University. We are measuring the indentation test. We are doing the indentation test to measure the fracture toughness. As you know, we had the crack propagation.
Yes.
And the time is really critical in this. And when we measure the length of the crack under the optical microscopic to put it in the ANSTES method, it's something really critical and might have a really bad errors and this stuff. Is there any standards or any specific times that, for example, we should, optimizing that, or we all, because we had the variety of also, results. Maybe I put it after 5 minutes, maybe you can measure it after 60 seconds. So how we can rely on the results?
That's why I told you that we must be careful and report all the data. For example, as you said, you indent and then you measure just immediately the crack size. And then you come after tomorrow or a week and the crack has grown, okay? People have used this to measure fatigue. If you look in the literature, okay? And I think this is unavoidable. So, for example, if you are pre-cracking, well, depends on what you intend, okay? Maybe if you want to use fatigue, this is one way of measuring. But for example, if you are doing mechanical tests like pre-cracking by indentation, I would wait until it stabilizes and then do the test, you know? At least you would know that you are not in a regime that it will have a stronger rate, you know. For example, you may do indentation and then you just look in the optical microscope and just by the humidity of you breathing, sometimes you see crack popping up, okay? So sometimes it's... Depending on the system.
To use it in other environments.
Okay.
For example, the water, the oil, these are all affected also. These are studied. I know that the different...
I think you have to do some first experiments. For example, when we indent, for pre-crack, we need to remove the residual stresses for bending. We could polish away or we could heat treat them, okay? So what we did, we put in a furnace 1 hour, 2 hours, 3 hours, 4 hours, 1 day, 2 days, and then we did some fracture toughness, and when we saw the fracture toughness became constant, so that were the conditions where we would, that would be the time that we relieve the residual stress. So I think you have to do some initial experiments to determine specifically for your glass what are the conditions what you want to study. Okay? When you have a steady rate, I think that's better.
We thank very much to Francisco.
You.
And move on to the final talk this morning.
Okay.
It's by Dr.
No,
Zhang
I just put here.
from Wuhan University of Technology in China. It's about glass and transparent ceramics from plasma melting. Dr. Zhang.
Hello, everyone. Thank you very much. It's my show time. I will tell you something different. I will focus on some not on the the new melting, I think new melting technique, and also the different geometries, because we are making some very tiny microsphere glass and ceramics. So since it's a school, I want to use teaching mode for the students. During my lecture, I will give a very short question for the students, just to keep you awake. Okay, I know maybe you are exhausted after the crazy night last night. So I just keep you awake. Okay, I will. And before that, I like to introduce something about our group research. Oh, wait, what's happened? Just the wrong button. So we are, as Professor Noto, he knows, we have many students, like 35 in my group, 2 professors including me, and we have several topics, not that close related. We just, as you know, we need to survive. We cannot survive without project. So we have to follow some industry requirement and also some basic research requirement. So the first one is a high-strength transparent glass ceramic for display cover protection. So in fact, this kind of glass, we have made it commercialized. We have some collaboration with the company and used it for Xiaomi. I don't know if anyone uses Xiaomi phone. The cover glass. We designed that, we made the compilation and make the product. The second one is about the glass ceramics for the IFSC ceiling. Anyone from short? Anyone from short? Germany short. I just want to tell you, your glass powder is too expensive. The glass powder from short. I can't imagine it. It like, as I know, the price is around 6,000 Chinese yuan. I think the price is pretty close to more or less 5,000 reals for 1 kilo. For 1 kilo, it's much expensive. So we need to develop ourselves, make it much cheaper. You know, Chinese can make the price much lower. You know that. So please tell your manager, consider this. Okay, the second one is the recently project we are applying. In fact, we have not got project yet. So we are trying to develop high toughness glass for microstructure design and nano defects. We combine the microstructure and maybe some nano defect in the glass together and to make the high toughness. For the students, it's a very simple question. I think Professor Francisco already gave you the answer. Do you know, in general, what's the fractal toughness for silicate glass? Normal, more or less number. The fractal toughness of silicate glass. Yeah? 0.7, you're right. More or less like that. I think Professor already, our target is trying to develop glass like 1.2, 1.5 glass. I think glass ceramics, it's easy to get this number, 1.2 or 1.5. But for glass, it's difficult. It's difficult. So I need your help for my project. And also, of course, Professor Noto. So the first one, the topic I will talk about the plasma melting. And also I make it quick. I'm doing some surface enhanced Raman spectral scattering based fiber sensing for trace toxic substrate detection. Nowadays, we can measure the mercury ions like 10⁻16 more per liter. It's trace content detection. And of course, the high modulus and low dielectric constant and loss fiber glass. We have designed glass for the companies, Isabella here, from the company. Maybe she's a bit absent. Are you here? Oh yeah. We have some collaboration with the Chongqing company. We talked the other day. So when you visit China, we can go there together for the glass fiber. And also the thin and high strength solar panel glass. Nowadays, we can make glass like 1.5 milliliter, but very strong, used for the solar panel cover protection. And also the AR coating on solar cell glass for high transparency. Several days before, Professor Noda sent me email and about the latest transmissions can get to 98. You send me the hyperlink about news. So nowadays we are getting to like 97 the transmittance, of course invisible range. So the last two topics we have a research center in Beihai. I will introduce that later. So I always think about something. We are doing some research. What a target for our research? If we can find something really new, I think it's our opportunity, and also make ourselves bigger and richer. As I think it's likely the morph glass you mentioned. I think several professors and students mentioned them several times. And here the very first morph glass, ZIF62 glass, it was developed by Professor Yue Zhengyue and his team in Denmark and also our university. So after that, for basic research, for example, glass forming and the different structure. For example, here is a short-range disorder, some new findings for the fundamental research, and of course, for applications for luminescence and for gas separation, and also for the batteries. Nowadays, they are doing some research on the battery based on the morph glass. So the next example is about the quantum dots in glass. Quantum dots in glass, the very first perovskite quantum dots in glass developed by our university, by Chao Liu, you know him. Yeah, by him. And the very first paper published in the Journal of American Ceramic Society. Then you can find different kinds of perovskite quantum dots developed in the glass matrix, and also for the growth process and how to change, and also for the applications, the LED display like this. I put the one picture here, just for show off. Just for show off. So do you know, any student know him? Mojin Bawendi, the MIT professors, he got the Nobel Prize for quantum dots. That's here, 2023. That's why just now I said that's a show off. I was so close to the Nobel Prize. Of course, I would do a similar thing. I would, when I have a presentation in China or some other place, I will show my picture with Professor Nato and all distinguished professors. And one more thing, many things mentioned Professor Nato. He developed a new glass theory about the new definition of glass and glass mesh. I quote here, I will not repeat. So the new theory makes better understanding of the nature of glass. As you know, in the past 20 or 30 years, it's a big question for understand the glass. What's the nature of the glass? So it's very helpful for his new definition, and also give some improvement for the glass research. So I take this example here as just for my consenting. If we can make some new theory and new glass materials and make some fundamental thing and for more research and production, then that would be great. That also is also my motivation for our very beginning motivation for we use the plasma melting. We are trying to develop maybe not that good. Not that good. We're trying to make some new glass system. Maybe in the future we can use that for example, the next slides. Aluminate glass formation from a novel melting technique. As we all know, alumina is not conventional glass former. We define it as the intermediate. But now there are some new aluminate glass developed. So if we can use a new melting technique to make completely new glass, like alumina, as I know, there are no melting, quenching alumina glass formed. It can be used. It can be formed using cell gel or chemical method. I will mention it later. So we want to make research to investigate the glass forming abilities for alumina and also the bulk glass preparation, structural evolution from metal to glass, so many thermal and mechanical properties and potential applications. That's the sample I want to do. Now we are going to the content. The glass forming pipe, I will have several topics. Glass formation process and modern glass preparation technologies, and also aluminate glass and ceramics glass, and also fundamental of plasma. I will give a very short because it's quite simple or complicated. So to understand plasma, because plasma almost everywhere. And of course, some sample for other glass microspheres from the plasma melting. Then I will give a conclusion. So the very beginning, I want to start this picture. It's very classical picture. As we all know, the glass from melt and to the super cool liquid and to the glass. I think we need the high speed cooling rate, and also if we change the cooling rate, we can make a different glass, and also the structure changes from the liquid to the glass. I think maybe all of you professors know better than me. Know this better than me. So we can make glass from melt. I want to say, before Professor Noto redefined the glass, I think from my understanding, the glass must be formed from melting and quenching process. I think, I don't know if you agree with this. So from liquid to glass is very important. And also, we need some critical cooling rate. And also, you developed the Jessica model for the cooling rate prediction. And here I list some critical cooling rate. Cooling rate here is for silica, a very low speed, but for the metal, we need very fast cooling rate. And also we think about for aluminate or aluminum glass, it needs very, very fast cooling speed. So what type of technique we can use? Air quenching and liquid quenching, drop spray for metallic and melting spinning, also for metallic glass, and for vapor deposition. Use a different cooling rate, we can get different glass. So, on theory, any materials can form glass if we give it very, very high enough cooling rate. So here are some examples of metallic glass, and even for amorphous water and amorphous carbon. It can form glass I think carbon from the deposition, but still based on the cooling rate. And also I found many papers about amorphous water. Amorphous water is very low, low temperature. So, as we know, glass also can be naturally formed. For example, the glass the glass from the, how to say, the lava? Yeah, lava, I think I'm right, the word. From lava and cooling down and can form glass here. And in Hawaii, there is a pellets hair formed from lava, volcano lava. And I have to mention here, I think in Hawaii, around 2016, it was the first time I talked to Professor Zanoto in the Pac-Rim conference. And then, you are so big, at that time I was so, it took me, in fact, it took me big courage to talk to him. Really, I still remember that. So, of course, from the moon, we can find glass. We can find glass. Here also some samples for glass for the moon. They exist like millions, even billion years on the moon surface. On the moon surface, I think it stay here a very, very long time. And one more question, not related. Do you know which guy? Who is? I guess your answer should be Armstrong. But in fact, it's Aldrin. I don't know how I spell his name correctly. Aldrin is the second one, the second land on the moon. So that's tricky. I know you will give the answer for Armstrong. He's the first one. But I will also say the first one should be remembered. I think the second one also very valuable. That's my opinion. So in the ancient time, making glass is very difficult. They use coal, and also I took picture from the Supreme Handbook of Glass, published to 2019. And for example, here some very, very old technology, even like we make the soap, then cool it down to make glass. And also here, and it's very difficult to make flat glass. When I was a kid, it's very rare for glass. We use paper to paste on the window to block the wind like that. So after that, I should start from here. I started in lab. In lab we make glass. Nowadays in the lab how do we make glass? Raw materials reading mixed. I think for students they know it very well. I will always tell my professor, I like this work very much. I don't know if you agree. So we make glass in laboratory, and sometimes we use this kind of equipment to make the moisture outside like that. It's a daily work for the students. And also, just now it's floating. The modern from around 1960s make that cheaper. The floating technology, I will not describe the details here because I need to focus on the microsphere thing. And here I need to mention, nowadays in China we can make ultra thin glass, like 13 micrometers. But it's for floating and also chemical etching, mixed technology like that. But anyway, the glass, orange glass comes from the floating method. Okay. Always sorry for this. And nowadays for the PV glass in China, you know, we make almost 90% of PV glass for solar panels. In fact, we use a calendaring. I just found the word. I don't know if even I don't know the word is correct. We make the glass melt between the two rows. I don't know. It took me a very long time to find the correct words in English. So nowadays we do like this. We can control the glass thickness between two rows, like that. So it is a technology to make the thickness and also the surface control. Normally we do not make complete flat glass. We need some patterns on the glass surface and to make better transmission. So, and also for the overflow glass for electronic glass manufacturing, it belongs to Corning. This technology of Corning, and also the downflow method to make electronic glass. And also, just now I mentioned that we made the glass for cell phone, for Xiaomi brand. This is a process of how we make glass. How we make glass? We make glass bulk, glass brick. I can say the glass brick. Glass brick, then move it to the big furnace and make it crystallized to form some nanocrystal inside to keep the transparency. And also, of course, mechanical process, and use cutting, slicing to the thin thickness, and also after that, we can make test. Oh, sorry, I cannot. After cutting, and we move another factory for polishing and iron change. We provide the very raw glass plate for the company. So it's a process. Now we are trying to use just now I mentioned the calendaring method to make this kind of glass, but it's difficult. It's very difficult to make this kind of glass because thickness of this glass. Who knows the thickness of glass for your cell phone? The cover glass. Who knows that? Glass ceramics. It's around 0.6 milliliter, 600 around more or less, because from generation to generation, the thickness completely different. The first generation Gorilla Glass, it was 0.7. Now it's fixed to 0.55 around like that, the thickness. So it's difficult cutting, and also it's difficult to make glass use this method. So before we talked about some silicate glass, and as I showed earlier, it just needs very low speed cooling. Very low speed cooling it can be formed very easy, not that easy, but it can be formed easy. But how about some glass is not that easy, more difficult. For example, here I showed samples like alumina and the ZiO2, like the melting point higher than 2000 degrees C. So we cannot use the natural gas to heating up for melting, and also we cannot use the electric for melting. But for some special furnace, it can get there. We need to find some new melting technology. So of course, for the glass without conventional glass former, as I mentioned earlier, make it more difficult. So that's why we're trying to make the new forming technology. About aluminum glass and ceramics, it's very common. It's very common for us. We know in a glass where you use a crossbar made of alumina and some other wares, and also of course alumina is very cheap. It's very cheap, and also we can make sapphire like this. We doped some different irons with the crystal, and also for the lens. If you use Apple Watch 11th generation, it uses the alumina cover. So of course, after the glass forming, the structure also can change with different coordination numbers, with different combination. So Therefore, for multi-applications for this relatively simple structure, so we consider how to make this kind of thing. And also here in the glass, and as we mentioned earlier, it used as an intermediate with a different content. With different content, the raw of the alumina in the glass is different, with different condition numbers. And also here it's true, the alumina can form the glass. This binary, how to say it, components for make a good glass with high glass transfer temperature and also the crystallization temperature, make it a strong glass. So here are some the new technology about ceramics. It also can be make transparent ceramics. Like as an example here, we use as CPF centering, alumina transparent ceramics, or the panel of the YAG transparent ceramics. In fact, I also think about that. Since it's more easier to make transparent glass, ceramics, sometimes when we make glass, make a mechanical performance decrease. So why we choose glass is I think someone brought the question during my talk before. So here we make different ceramics for various applications. And also here, as I mentioned earlier, some people use the chemical method and the Sojal divider, they can make alumina glass. But here, I must to mention here, the glass transition, as reported in the paper, alumina glass transition is only 400 degrees C. In my opinion, it's almost impossible. I don't know how do you think? Yeah, pure alumina. Yeah, pure alumina. In fact, the paper from the scientific report from a Japanese team, they analyze structure like this. But the glass transition, I think is impossible. Maybe not pure. Yeah, I think a lot of water inside. Yeah, but according to the paper, they said it's pure alumina glass. I think it's impossible like this. We need to move on. And nowadays, why we choose aluminate? Compared to silicon glass, it can provide pretty high hardness, and also the modulus. Of course, the fracture toughness. And also the phase diagram here, it shows a very high melting temperature, as I said earlier. So we use before that, I introduced some professor mentioned we use the aerodynamic levitation to make glass and make very successful. And in our university, we made of alumina, calcium oxide, and tantalum oxide, this triple component glass, and make the glass ceramics and get the very high hardness and also the modulus. So we want to use plasma, but what is plasma? So as from the definition, and the definition is the fourth state of the metals. Fourth state of metals is including ions, electrons, and also the neutron atoms inside. It's a mixture. Once we call it plasma. It's very common in our surroundings and also in nature. Sun is maybe it's the biggest plasma sphere we can see, but we cannot go to sun to melt glass. There's a black joke I want to brought here. Someone told me you can go to sun to melt glass at night. It will be cooler. I don't believe. I don't know how you. It's a black joke. Just forget it. So it's very nature, and also the plasma, as we mentioned, the most important thing is to make ionized in the. It can be used electro discharge with high voltage, and also use thermal energy with very high temperature. That's why plasma generates the high temperature. And also we use the radio frequency waves, microwaves or lasers to generate plasma and to make ions. And also the torch, like we daily use. We daily use like this. The structure outside, the flame structure like this. And as we know, the central part should be the highest temperature. We know it from the elementary school. And also the temperature distribution from torch. From torch is a typical sample, but based on the energy consumption, and also it's like it can get to around 1,000 to 20,000 degrees C, like that. So it almost can melt everything. Since it's also very high temperature, it's possible to make a very high speed cooling rate. So that's the basic thing we want to make glass, like use plasma melting. And here, as I mentioned, the fundamental difference between conventional heating, it uses electricity to create plasma as a medium for heat transfer, provides intensity hot, clean, and precisely controlled energy source. So we can keep our melting materials. They are resistant to the traditional furnace. Here is a sample we made the plasma, just 15 seconds. The plasma torch like this. The central temperature, in fact, we measured is around 8,000 degrees C. Not that hot. It depends on the power supply. I think just for my experiment, it should be enough. 8,000 degrees C. And also the plasma can be used for like coating and surface treatment, and also cutting, many applications. This instrument in our lab, we bought it from Canada. From Canada. And this lab uses the plasma torch here, and when we put the raw particle inside the plasma, and it will melt in the central part of the torch. And when it goes down, going down with the temperature in the cooling chamber, it can be solidified and it form the sphere with the surface tension. With surface tension, then we can get the spheres. In fact, the instrument includes two parts. The first one is to make microspheres. The second one, we want to use for coating, but we barely use that. For coating. So there are some benefits for the plasma melting. For example, high temperature, electrodeless heating, high-speed quenching, and also contactless melting. So just very short about macrospheres. The definition of macrosphere is about in macro or nanoscale solid or hollow macrospheres. It's, for example, low density, high mechanical strength, low thermal conductivity, and the corrosion resistance depends on the corporation. And also it can be used much more like I listed here. Electronic device, biology, 3D printing, much more. I think it's very useful. It will have a very hot topic, including bioactive. I think nowadays some people may making metallic macrospheres for biomaterials. So it's very useful. That's why we want to develop technology for melting. Normally, sorry, I need to. Normally, the macrosphere can be prepared in gel. It can make nanoscale from several nanometers to hundreds of nanometers like this. And also, we use a flame torch with pretty relatively low temperature to melt something and to form the macrosphere. And the spray and dry, we can get the coarse surface sphere. And also, I mentioned earlier, we can use aerodynamic floating melting to make the sphere, but it's milliliter scale. Milliliter scale, and we just only can make one sphere one time. So it's difficult to make the production. So before, we did some experiments in our lab. We want to use it for the silica and silicon gas microsphere. And we check the many parameters, like I showed here, particle size, and carrier gas, and the feeding speed, and dispersion gas. Then we can get the spherization ratios. So we optimize the parameters, instrument parameters, then we can get the transparent ceramics like here, and also for pure silica, we can go very close to the glass with some minor crystal inside. The diameters is around 40 micrometer, around 40 micrometers, and of course we can get some other silicate glass. I will not repeat it here. We change the composition of silicate glass. It's easy to get melt and to make glass. And later on, we want to use a microsphere to some floating equipment. So we made some hollow silica microsphere. We put some foam agent inside and use plasma and to form some hollow structure like this. We can make the very thin wall hollow microsphere, and the density is around 0.4 grams per centimeter cube. It's lighter than water, much lighter than water. So we can use for the floating instrument. So later on, we focus. After that, we consider what's the new materials we can use for this torch from his high temperature and probably very high speed quenching. So we designed the composition like this. We use a different oxides, like alkali earth oxide and rare earth oxide and ZrO2, with the different compositions, and we designed the composition with the lowest eutectic melting point and the stoichiometric proportions. We designed the composition and use it for the melting to make probably transparent ceramic or glass. We don't know it yet. The very first we designed the microsphere like this, aluminum calcium oxide, because it's very common glass. Even in the glass world, it's very famous. It's easy to form glass with a very broad glass forming region. In the phase diagram like this, it can form glass. It even use a common method. So it can it will be prepared to use this method, and also the microstructure of this glass have been well analyzed. So we optimized the parameters, and finally we made this kind of microsphere with good transparency. Unfortunately, we cannot measure the transmittance because it's so small. In fact, last year I asked Professor Nalin if it's possible to measure the transmittance of this small range. So we're still trying to find a way to measure this tiny microsphere transmittance of this. So the more interesting, the glass formed in this area with where is the laser pointer? Difficult. It's like this. Alumina is 36 and alumina and 64 calcium oxide. Calcium oxide. We made this kind of glass and we analyze structure. It obviously the alumina surrounding changed the coordination number. And more importantly, I think the harness and modulus change a lot. So we can get like 130 gigapascal modulus and around 13 gigapascal harness from this kind of microsphere. It's reasonable result. And later on, we change to the magnesium oxide microsphere, and also we can optimize the parameters. We can make the similar thing. And the structure is ceramic. It's a ceramic, transparent ceramic, and also the alumina surrounding changed with the ratio, the ratios of the alumina and magnesium oxide. And also here, we can get even better hardness and modulus. It's like this. I think it's like the highest can get to 15 gigapascal hardness, because it's, I think, the bond between magnesium to oxygen is much stronger. So we can get this way. And also we move to the rare earth ions because it's very famous YAG. It's very famous YAG, so we also try to make the microsphere like this. And also we analyze, it's a transparent ceramic microspheres. Of course, the chemical shift of the alumina changed a lot of Raman effect is not good. Analysis is not good. And also we analyze the crystal phase, and also the harness like this, the gigapascal. So we want to improve the mechanical properties of these microspheres from the different components of the microsphere. So then I make quick, then we make the lithium oxide. We make transparent or translucent microsphere use this way, and we can get the pretty similar result. It's like more than 20. And also, of course, it transparent ceramics like this. We do, if I want to see, we are not just playing the completions. We are trying to find potential glass forming region. Is some experiment about that. Of course, nowadays we are improving our instrument. In the cooling chamber, we are using the water cooling and also liquid nitrogen cooling. Liquid nitrogen cooling to get gas to provide enough cooling rate and to make glass. So there is some experiment we did before to make better one. And also, of course, the GD203. We also make the glass like 22 gigapascal and also 0.2 microspheres. In fact, we made it pretty earlier, like 2 or 3 years before. But we want to make very high quality microspheres. In fact, one year before, more than 1 year before, you provided an broad idea. We can mix the microsphere inside the glass. Okay, sorry. Inside glass, but nowadays when we improve our preparing technology, we want to get all clear microspheres. Then we can design the high refractive index gas matrix and mixed with the microsphere together to make stronger bulk gas ceramics like that. I know you're waiting. Okay. And also, finally, we make that one, and here it showed very high hardness and modulus for this kind of microsphere. Of course, it's a ceramic. It's just mixed of the alumina and the ZiO2. It did not form the compounds like before. So we still have many problems to solve. And also, and we know that the cooling rate depends on the diameters, so we decrease diameters and try to find the possibility to form gas. And here, we use a different precursor preparation method. Anyway, we found some glass phase inside, not pure ceramic anymore. But when it forms glass, the mechanical properties decrease a lot compared with the ceramic phase. So that's the question I brought before. Okay, then later on we want to make glass, we move to the alumina. We have no other choice, we put some silica inside again. Finally, we made some not very good, we need like 20% alumina inside. I can make the glass like microsphere, some nanocrystal inside. I'll make it quick. And also here, some results, it decrease the mechanical performance. It's likely the common silica gas. And also, recently we put some magnesium oxide in the glass. Finally, we can get for X-ray diffraction, we get clear glass. Use this one. You use this composition. We can put more percent magnesium oxide inside, but based on the 10% alumina and the 90% silica. Too much silica inside. But anyway, we got glass. Use this technique. And here is the harness and the modulars. It's not that high anymore. No, not that high anymore. So it's very difficult to make decision. Is glass more important or the performance important? So anyway, we made a different kind of aluminate microsphere plus melting and harness, and we can get this one, this big, and with formation with a smaller diameters to save time. And also we are planning to do something, as I mentioned earlier, for the microspheres, for multifunctional transparent ceramics, and also the special glass formation for plasma melting I mentioned at the very beginning. And also low temperature sintering for bar glass and transparent ceramics anytime from Eduardo. I think when we make clear microspheres, we can do it together and use sintering technology and we make it bulk. And low time, and also organic compounded with microspheres, and also for commercial use. Okay, this is our research, but maybe I run out of time. I'll just very quick share with our university. And the Wuhan is here. Several of you have been there in the center of China. And here our university is a top university. It's ranked around 40 in 1,000 university in China. More than 1,000 university in China. I think it's a good one. And also the materials in our university, very long history on glass, especially on silicon material research. And also we have a state laboratory. This is a student number. We have very big number. I think it's for the undergraduate students, it's around 3,000, around 4,000 graduated students. It's a very big number for the students. So that's why in my group I have many universities. And also, well, I will keep this one our major. In fact, about materials, we have several advanced, several silicon laboratories. In fact, we have three. Including this one, silicon laboratory advanced glass materials. The director is Shopeng. Many of you know him. And we focus on the fundamental and application research. We supported by the CNBM and University Science and Technology of China, University Science and Technology of China, and also our university. And we focus on different glass research, including from the very basic science, very basic science. For example, recently we submit a project about the glass relaxation. That's why I need Ricardo, of course, are not. We want to make closer collaboration based on the project. We need your help like that. And also the glass surface, also the equipment and manufacturing process, advanced glass materials for different applications, and for processing. And as I mentioned earlier, we have a research center in Beihai City. It's the south of China. It has a very beautiful beach, very beautiful beach. I'm trying to make our winter school in there this winter. I'm trying to, but I'm not sure. The most important thing is in that area, it has very high quality sand, around 1.8 billion tons. Yeah, we invited seven largest PV glass companies, and now they can make 10,000 ton PV glass every day. Every day. So now it's the second largest PV glass base in China. I think also in the world. So, and we did some coating research here, and also here the answer, easy gland. Here for everyone. I think Professor Zanoto already made an official announcement in his LinkedIn. I made the screen. This is the screenshot here. You made an official announcement. So we will make very close collaboration for basic research and also for the application research. Here is our research team. Just not all. And here is the Beihai City, in a research center in Beihai. And here, the handwriting note, I always keep it and show it. Because Professor Nanoto, he made a name, Easy Glad name. When we went to Beihai together, we discussed in a Starbucks coffee store, in Starbucks, and we used a receipt paper. He wrote name there. So at that time, we named it Z-Glad, not E at that time. Later on, Professor Nodo, he made a decision to make it easy glad. That's also our attitude about research, to make happy and to make it more efficient and happy. That's our attitude. And also, we need some students and postdoctorals, but you need to get approved by Professor Zanoto. He is the boss now. One last thing about our winter school. 2026 winter school, it will be in Wuhan or Beihai, not that yet, but I want to make it in Beihai. It depends on the funding support. And also we need to get permission from Anna. You are TC23 chairman, so we need to get your permission. It's like that. So the chairman is Professor Noto and another Korean professor, Professor Hao Zhong. Maybe many of you know him. Okay, that's all. Thank you. Thank you very much. Thank you.
Yeah, so we make sure that we don't miss the lecture of Professor Zanotto at 13:45. We have to limit ourselves for the discussion. And first of all, we'd like to thank you very much for introducing us into the fascinating world of conditional glass formers.
Yeah, thank you.
And now maybe we'll take one quick question here.
Yeah, please. Marcos?
It's just a quick question about this system where you showed that you have aluminum, silicon, and you add magnesium. Yeah. I didn't understand that you have A1 to A5. Which one has more magnesium there?
I will check.
When you go to A5, because when you go to from 0 to 5, I think that you are increasing magnesium, but the silicon is getting more coordinated.
I think it's more magnesium oxide, you say.
So, but increase the polymerization of the network when you add magnesium.
Yeah.
It's interesting.
Hi, Professor. Thank you for our
yeah.
conversation. And I would like to do more questions, but I'll be quick. So
Limited time, okay. We do not want to delay your lunch.
Okay.
You're hungry.
So is the energy consumption of the plasma lower than the comparable, lower or comparable to the furnace?
I think it should be lower. In fact, a very interesting fact, we bought each instrument, and the very beginning, we want to use it for helping the melting furnace for floating furnace. You know, we put some comment can be melted in the plasma torch, then going to the tank, the melting tank, and it will be energy saving. And the very beginning, we tried and also we confirmed, but it's difficult to make mass production.
Okay.
You know.
Got it. But the atmosphere is not controlled, right? The atmosphere of the plasma is not controlled, right?
I think it can be controlled. Yeah,
Okay.
from the reducing and to oxide atmosphere. It's based on your carrier gas. If you use H2, that will be reducing atmosphere. If you use oxygen, you know, it's clear.
Okay, thank you.
Yeah.
Okay, so this concludes our morning session.
Okay.
And
thank you.
let's thank again all speakers. Please be back on time for the.
Well, thank you very much, Professor Helmut. A very, very short and important announcement for tonight, because I already made one here, but nobody was here. You are all sleeping early in the morning, most of you anyway. So tonight, if you feel, you know, energetic enough, we have a cocktail. It will not be a formal dinner. That's Brazilian snacks and drinks. The buses will leave between 6:30 and 6:40. By 6:40, the bus will leave. So if you're there, it'll be a great pleasure to host you tonight for this cocktail party, okay? Between 6:30 and 6:40. From the hotel, both buses from the Markling. Good question. If you're coming by car, you need to send Laurie the plate number and the driver's ID, because there's security to enter in that place. It's a high technology park, so there is security. By car, plate number, and driver's passport number or driver's license to Laurie, please. Okay, that's good tip. Okay, see you soon. There's an important talk after lunch. Don't miss it.